uzman sunumla devam edeceğiz çevrimiçi katılımcımızın. Profesör Doktor Suresh Pillai, Professor at Texas A&M University and Head of National Center for Electron Beam Research in USA. The presentation is electron beam technology will be a disruptive technology in the environmental industry. Dr. Pillai, can you hear me?
Yes.
Okay. The stage is yours. I can wait to say you the presentation is ok.
Can you hear me?
Yes, we can hear you.
Okay, let me share my screen.
Okay.
And let me make it full screen. Does that work?
Yes, okay, thank you. The floor is yours.
Okay, thank you very much. Thank you, Dr. Omar, and thank you for the organizers for the opportunity to speak at your workshop. It's indeed a great honor. And sorry yesterday because of the scheduling time, I couldn't be there yesterday to make the presentation. And thank you once again for the opportunity to present this morning. So as was announced, the title of my presentation is on electron beam will be a disruptive technology in the environmental industry, specifically in the wastewater and drinking water industry. So we all know, hearing yesterday's presentations, etc., it's not a question whether electron beam technology will work in the environmental industry. And we have data going back to the 1980s, work done in Boston in the United States, showing that you can treat wastewater with electron beam technology, not only in the US, but in Canada. Then there was a pilot scale facility in Florida, and then thereafter in 2011 in South Korea, in China, and then more recently in China has gone on to make a pretty large investment in using electron beam technology for hospital wastewater, industrial wastewater, and from what I understand, their scale is currently at 30,000 cubic meters per day. So that's really impressive as to what is going on in China. So, but why isn't it happening in a larger scale? I mean, we know the potential of this technology for many years, for many decades, but how do we make this technology truly disruptive? And for disruption, when I mean disruption, it is something that when the larger technologies are not aware of this newer technology, quote unquote, newer technology, and they are surprised by the speed in which this technology changes everything. At least in the United States and probably in many other countries, many decision makers in the environmental industry do not understand this technology. This is indeed a travesty. This is indeed unfortunate because even many experienced environmental consulting engineers and consulting companies are totally unaware of this technology. They mix it up with UV technology and other technologies and ozone, etc. So the question is, when can this technology move from prototype to larger scale? And when I mean larger scale,
progress.
And when I mean large scale, it's meaning that it can serve. What happened here? When it can serve 100 million gallons per day volumes, because in a city like Chicago or San Francisco or Los Angeles, we are not talking about 100,000 cubic meters, etc. We are talking about 100 million gallons per day type volumes, and what sort of technology is needed. So the presentation today, what I want to make is talking about specifically a changing view of biosolids or sludges, and then specifically talk a little bit about the data we have collected over many years on the response of microbial pathogens in sludges and effluent to electron beam doses. And then talk specifically about enhancing methane production by electron beam technology, and discuss some of our work that we have done in terms of using this technology, the economics of e-beam technology for sludge treatment to enhance anaerobic digestion. And then finally end the presentation by discussing very briefly what is needed in terms of the technology and outreach. So if you look at the history of biosolids management or sludge management, in the 1970s to 1990s, the focus was on disposing of the sewage sludge in landfills or other applications in land application programs. In 1990s, the concept of beneficial reuse became very prominent, at least in the United States, where rather than just disposing of the sludge in a landfill, can you use this for very particular land applications like golf courses, vegetation, revegetation programs, etc. In the early 2000s, there was a big focus on bioenergy, methane production, and now we know that it's more not just limited to methane production, but also in terms of other resources. So the focus now is not just energy production, but also what is a value-added products. So the contemporary view is municipal sewage sludge as significant pools of energy, substrate, nutrients, and water. So when we think of sludge in this context, that there's a lot of energy, there's a lot of water, and there's a lot of nutrients available, we should stop thinking about wastewater treatment plants, so calling them wastewater treatment plants. And as you probably know, all around the world, there's a big movement to even change the names of these facilities into sustainable resource recovery facilities. So it changes the concept from wastewater treatment to sustainable resource recovery facilities. And that's because there is a need to exploit or harness different technologies for trying to recover the energy, nutrients, and water as much as possible from wastewater treatment, from waste streams. So we now know that e-beam technology applications in the wastewater industry can go for biosolids treatment because in the US, the EPA recognizes e-beam technology or gamma or X-ray up to 10 kilograms as called as a Class A process, as a process to further reduce pathogens. We all know that it's effective against a variety of microorganisms. There are a number of studies which show that it's an extremely green technology because no chemicals are being used. And more so, it is rather than talking about this technology or the process taking hours, it is done in virtually minutes. And then depending on the dose that you're interested or the applications you're interested, you can calibrate the dose. We also know that, at least experimentally, that you can use it for biogas production. There's work that's gone on in this area in the US, in Poland, and in Korea about enhancing biogas production. It'll increase, not only will it increase biogas production, but there's also other value-added benefits or value proposition of e-beam technology or sludges, including reducing the viscosity, reducing the digester residence time, and also you can actually get Class A biosolids that if you combine it with digestion, you can get highly stabilized Class A biosolids. In addition to that, in effluent treatment, you know that we can use it for a variety of similar applications, reducing the chemical pollutants, the biological hazards, etc. And then the ozone that is produced during the e-beam process can also be harnessed or can also be combined with other processes to enhance the treatment efficiency. So we know this can be used in all different areas. These are studies we have done in the past to look at sludges, the organism, the microbial load in these organisms over in different locations. Let me just lay the point. Let me use the laser pointer. As you can see, that fecal coliforms and E. coli, etc. If you look at the most probable number in 4 grams, these are 2 locations in Texas. As you can see, the numbers are quite variable. Salmonella aerobic spores, it's very high. Clostridium is relatively high. Enterococci is a high. E. coli is relatively low, depending on 10 raised to 3, depending on the location that you are discussing. So it's not that all these organisms are always present at 10 raised to 8 or 100 million or 1,000 million organisms. And then when you look at the virus levels, once again, it's not that all these sludges contain, a million virus particles per gram, etc. It can actually be present, relatively present, sometimes below detectable limits. So you look at culturable viruses, and many times you're finding them below detectable limits. And in some of the times we find these somatic coliphages in relatively low numbers. So the take-home message in these slides is that we have to be very pragmatic in terms of what is the log reduction that we're trying to achieve with viruses and with bacterial pathogens. In studies that we have done with biosolids that we have worked with, and this was published many years ago, we know that you can get, with a very low dose that you can apply, you can have complete elimination of E. coli population, salmonella population, the anaerobic spores, the aerobic spores, as well as the viral enteric viruses. So with the type of, and then if you apply the EPA standard of 10 kilograms, you can see with the bacterial populations, you can have significant log reductions, and aerobic spores, which are the most resistant of the organisms, you can get 2 to 3 log reductions. And then with viruses, you can sometimes get up to 4 log reductions, 3.8 log reduction of poliovirus or rotavirus, significant reductions at 10 kilograms. So if you apply the technology just with dose to eliminate microbial pathogens, in my opinion, in 2022, that really doesn't serve or doesn't really harness the technology enough. We need to figure out how can we combine this with other processes that's currently taking on in the wastewater treatment plant. So anaerobic digestion is a key technology in a number of wastewater treatment plants around the world. There are different methods of hydrolysis. There's the thermal hydrolysis process, also called THP. The other patented trade name for this technology is called the CAMB process. There's also biological hydrolysis, there's mechanical hydrolysis, and chemical hydrolysis. So I want to focus specifically on the thermal hydrolysis process, or THP, which is, in my opinion, the most fastest growing hydrolysis process currently in the world today. So this is the technology. This is the technology that is really a lot of wastewater treatment plants have been investing millions and millions of dollars into this, and this is a technology that really want to disrupt. And this is where the electron beam technology is really poised to disrupt. So CAMB process, or the thermal hydrolysis process, is a very high temperature process, 150 degrees to 170 degrees Celsius, very high pressure, 6 to 9 bars pressure, a reaction time of 20 to 30 minutes, and then you need to put in dewatered sludge about 14% to 17%. As you can see, this is a very energy intensive process. The carbon footprint of this technology can theoretically be high because you're having high temperature, high pressure, and then you need to also have dried 14 to 17% dewatered sludges to go into it. So the result of a CAMB process is that you have decreased viscosity. It allows sludge mixing at higher concentrations. It decreases the digestion volume. Also, at the end of this process, you get a sterilized sludge and you get enhanced anaerobic digestion with increased volatile solids reduction, improved biogas production, and reduced mass for further processing. So the installation of a CAMB process like this in a large wastewater treatment plant, for example, in Washington, D.C., a few years ago was close to about $300 to $400 million investment, where they invested this CAMB process into the facility. So studies done by Korean investigators back in 2003 showed that electron beam technology can be used to recover energy from municipal sewage sludges. So you can see here, even very low doses, 6 kilograms, you can get increased soluble proteins compared to the control. And then you will have also this waste activated sludge. You can also have the thickened sludge as well. You can have increased soluble proteins, and chemical oxygen demand as well increases. Also, those studies showed that when you apply high doses, or exactly relatively low doses, you can get a tremendous breakdown of the sludge flocks. This breakdown of sludge flocks is extremely pivotal in this technology, because the faster you can break the sludge into these flocks into smaller pieces, the better the hydrolysis takes place. So this is really where e-beam technology now kind of competes directly head-on with CAMB process. And even at very low doses, 5 kilograms or even 10 kilograms, you can see the sludge material is completely hydrolyzed and is much more homogeneous. And in the same studies done by Shin and Kang in 2003, where they looked at anaerobic digester, they had 4 different types of digesters, A, B, C, and D. And in each of them, they had residence time of, this is a controlled digester where there was no electron beam treatment, and the sludge was kept for 10 days, 15 days, and 20 days. In digester B, the dose was 1 kilogram, same 10, 15, and 20 days. And in digester number 3, it was 10, 15, digester 3 is 3 kilograms and digester 4 is 6 kilograms. You can see that even with a dose of actually 1 kilogram, even after the residence time, if you look at the 20 days of control in the controlled digester without any air e-beam treatment, you get about 82 cubic liters of methane per day after 20 days of residence time. And you can see here that even with 1 kilo gray, you can see the significant increase in methane production with just 10 days of residence time. You have 175 liters of biogas per day, of cubic meters per day. So you can see here when you just increase it to 1 kilo, just applying 1 kilo gray, the significant increase. And not only is the increase in methane production, but also the reduced residence time. So reduced residence time translates into dollars significantly for any wastewater treatment plant. As you can see here, 1 kilo grade, 3 kilo grades, and even 6 kilo grades you can get increasing, but it plateaus out at a certain dose that you can see here. Whether you keep it for 10 days or 20 days, the amount of methane that's produced is the same. So there's a case of diminishing returns as you keep increasing the dose or you keep increasing the residence time. But the take-home message here is that even with doses as low as 3 kilograms and a shortened residence time of 10 days, you can far exceed the amount of methane production without an anaerobic digestion. So that we know now has value. The other big important area of concern is water reuse. All around the world, water quantity becomes a driver for change, and a driver for a lot of rethinking. And in water reuse, there is the different types of water reuse. There's a de facto water reuse that is currently going on around the world, where you have from the consumer's wastewater plant goes into a wastewater treatment plant, and then after a treatment plant, it then goes into an environmental discharge, either into rivers or etc. And then after this, further downstream of this environmental discharge, there's a drinking water treatment plant that takes that water from here and then treats it and gives it back to the consumer. So this is the current water reuse. There's a lot of indirect potable reuse, where the water from the wastewater treatment plant, the water goes in advanced wastewater treatment plant, a water treatment facility. This is really a drinking water treatment plant. So here you have tertiary treatment like ozone, etc., UV, membrane filters, etc. So the water that is coming out of this particular treatment plant is equivalent to drinking water standards. But given the concern or the social perception of consuming water coming from a wastewater treatment plant directly into the consumers, it is actually, unfortunately, being back again into an environmental buffer or pumped underground deep into the aquifers. And after a significant number of residence time of maybe calculated to be in years, this water is then pumped up for another drinking water treatment plant, and this drinking water treatment plant goes in here. So you can see there's a tremendous amount of waste of resources between these steps, because you have an advanced wastewater treatment plant or advanced drinking water plant, and then there is two treatment plants here. The more recent one is called the direct potable reuse, where from this advanced drinking water or wastewater treatment plant, it actually goes directly to the consumer. This is nothing new. This has been going on since the 90s in South Africa, and now in a number of cities in the United States, this is being considered. Or sometimes from this advanced treatment, it goes to another drinking water treatment plant and then goes to the consumer. So you can see here, this particular environmental buffer has been completely bypassed, because it goes directly from an advanced wastewater treatment plant to a drinking water treatment plant and then directly to the consumer. Or like in cities or in states like in California and Texas, where there's significant water shortage issues, the water can actually potentially go directly to the consumer. So in these instances, in water reuse, there are concerns of chemical contaminants and microbial contaminants. The chemical contaminants are disinfection byproducts like bromoform, bromate, chloroform, trihalomethanes. There's also household products like bisphenol A, PFOA, PFOS, as well as estrogenic compounds, antibiotic residues. And there are studies that have been done both from our lab and in other places in Europe and in Asia, where this e-beam technology has been shown to be very effective at breaking down many of these chemical contaminants. And then the microbial contaminants are the concerns in water reuse is enteric viruses, especially rotavirus, hepatitis A, and noroviruses, enteric bacterial pathogens. And then sometimes during the pandemics or epidemics, you have to worry about the coronaviruses or Vibrio cholera or SARS coronavirus. Or also sometimes we also have to concern about protozoan parasites like Cryptosporidium giardia or Cyclospora, because they have to be treated, because they could survive this treatment process either here or here, and then you need to have a technology that can take care of these two contaminants. Fortunately, because of the of the rich literature that's available around the world, we know that most of these things can be treated with electron beam technology. Most of these pollutants can also be handled or managed with electron beam technology. The question then is, how do you actually incorporate it? So we have done some studies in wastewater effluent. You can see 1 kilogray, the log reductions of salmonella viruses. But this is in 1 kilogray. You can see very little viruses are inactivated, which is not surprising. And protozoas, very large numbers of protozoan oocysts and cysts can be inactivated. But if you apply 10 kilograys, you're then applying, you can get the log reductions that you're achieving. So for water reuse, the log reductions here, these types of pathogen controls meet the water reuse standards. The other concern that's now coming on because of climate change is toxic algae. Toxic algae could be toxic cyanobacteria like Microcystis aeruginosa, which could impact recreational water bodies or in fact large reservoirs or even the ocean. So a harmful algae is a major concern in the United States and around the world. So we have done some work in this area looking at the degradation of Microcystis LR, which is the toxin from the algae Microcystis aeruginosa. At very low E-beam doses, the toxin is highly degradable. As you can see here, even with a dose of about half, even less than half a kilogray, you can have significant reductions of Microcystis LR. 0.3 kilograys gets you about 85% reduction. But you have to also keep in mind, in the case of toxic algae and toxin, it is not only just the toxin that you have to be worried about, but also the actual algal cells. And we have also shown in the papers that we are publishing that it's very effective against the algal cell as well. So we did a study to find out does this technology that's the location of where the water is collected from, and in terms of the chemistry of the water, have any impact on the degradation efficiency. So we collected water samples from about 22 or 25 locations around the United States. Obviously, these are actual surface water. We spiked them with concentrations of Microcystis LR. And then we ask the question, you apply 5 kilograys, what's the reduction? So we find that in all these locations, even at low doses, 5 kilograys, it breaks down the toxin with greater than exceeds 99% in all the samples. There were no trends that were observed in the water quality and degradation, which is good news that it degrades this toxin as well. So when you look at water reuse, as I mentioned below, we have shown with hepatitis A virus, rotavirus, and salmonella, the water reuse targets are for coliform bacteria, you need to have 9 log reductions, for viruses, 8 log reductions, and Cryptosporidium oocysts is 5.5 and 6 log reduction. This is the water reuse targets in the United States. So the doses that can be used for reuse targets is, you're now looking at viruses of 15 kilograys, 2 kilograys, and 2 kilograys for bacteria. The viruses require 15 kilograys. So this is where we have to look at understanding what's the technology that's available that can deliver 15 kilograys in water that is going at very large volumes. So we compared the cost of anaerobic digestion, aerobic with EB-mediated aerobic digestion to the CAMB process. So we binned all the treatment plants in the United States as either 10 million gallons per day, 10 to 100 million gallons per day, or 100 million gallons per day. And we looked at actually electron beam at 100 kilowatts beam power pre-treatment. So you can see if the treatment plant is larger, if it's 100 million gallons a day, it's only $293 per dry ton, while if it's a smaller treatment plant, it is 10 million gallons per day. This is not surprising because I think all of us in this room or in your room there know that this technology is really meant for very large facilities. So you see that as you increase the size of the plant, the costs come down. And what is also interesting is that when we compare the electron beam at 100 kilowatts beam power and thermal hydrolysis, you can see it's almost half or a price of the CAMB process. So this is where I'm confident that it can be a disruptive technology, the CAMB process. So we then further looked at different types of configurations at 10 million gallons a day at 100 kilowatts beam power and 400 kilowatts beam power. As you can see here, as you increase the treatment plant to 100 million gallons per day and with very high beam power, and you have a dry tons per day of 70 dry tons per day, the total cost per dry ton drops significantly from $311 to $72. So the take-home message here, and this we've done the capital costs, etc. Of course, this is the capital cost. All this is pre-pandemic. So I just want to show you that the price dropped significantly. It's a very large facility and very high beam powered machines. We actually looked at, we also calculated the costs when you couple this with stabilization, because you not only have to be the sludge treated, but it also have to be stabilized. We can see the cost of 10 million gallons per day cost is about total is $440, and 100 million gallons a day is a cost only 133. But if you compare these to 171 to 133 to the CAMB process, you can see here the CAMB process is about $500 a dry ton and $386 a dry ton, and the E-beam process is almost half the price. So you can see a significant cost savings with the E-beam process. But the problem is, why isn't this being adopted widely? And I think very many of us understand now the technology is not there. In my opinion, what we have today with the dynamitron, etc., these are good technology for showing the potential, but we really need accelerators in the 1 megawatt accelerator scale, high energy that can deliver 10 kilograms, 15 kilograms, etc. We need very high beam power machines, and these machines are not, I mean, they are available at an R&D level, at the national labs, at the Fermi national labs, etc., but commercially they're non-existent. We still have not optimized, we still do not have all of the process trains developed, matured for handling high volume sludges, biosolids, effluent, are still in their infancy. We still do not know how to deliver these products under the beam and to meet these high volume demands. More importantly, which is for me very unfortunate, is the practitioners in the water and wastewater industry have limited information on the technology. And this is, I think, Dr. Omar has mentioned this for many years, and I looked at this more recently. If you look at Metcalfe and Eddy, which is the Bible for wastewater treatment or drinking water industry professional, the disinfection section has nothing about ionizing technology. It stops at UV. So, you cannot expect the consulting engineers to talk about or to adopt E-beam technology if they don't even know what the technology is. So we need to edit on the next edition of Metcalfe and Eddy. We need to have chapters on electron beam technology and X-ray technology and gamma radiation technology, if the case may be, but we definitely need sections on ionizing technology. And then more importantly, is we need more facilities around the world as proof that the technology does indeed work. Fortunately, now China has demonstrated that technology is applicable. There's a large number of facilities, so people can go and see how it's done. But we need more and more applications of flue gas, of sludges treatment, etc. So I think I'll end with this slide, and I'll thank you very much once again, Dr. Omar and all your colleagues in Turkey for the opportunity. And I'm unfortunate that I'm not able to be there in person. Thank you very much.
Thank you for your presentation. Is there anybody, any question? One question. Dr. Pillai, there is one question in our
Yes, please go ahead.
hall.
I cannot hear you, but.
Maybe you can ask how many units are commercially being used in USA?
Şu an çalışıyor olabilir mi?
Hello.
Yes.
Good morning, Dr. Pillai. And compliments for nice presentation. So we would like to know how many units are working in USA for sludge hygienization or wastewater treatment based on electron beam or gamma radiation.
That's a very good question. The answer is also very easy. It's zero. We do not have any facility that's currently operating with electron beam or gamma radiation. The last facility that operated in Florida was in the 1990s, late 1990s. But since that project, there's really zero facility operating on ionizing technology.
what is the most probable reason for this kind of situation? Although radiation technology is known for ages now, but still no output as such. What could be the reason for it?
The reason is twofold. One is many people see and there was a very interesting workshop, I think, organized by Sunil when he was at the IAEA, and Omar had attended it as well. The people who have to adopt this technology have to be the consulting engineers and the engineering consulting companies. When they get a project to install a technology, let's say for enhanced sludge digestion or anaerobic digestion, they are very conservative. It's a very conservative industry. So they go to a technology that's time tested. There's a number of historical, there's a lot of case studies. And they would go something to CAMBI process because that's now available. You cannot expect consulting engineers or consulting companies to go into a technology where we have very little information about. That is operating at very large scales. And so it's a combination of a couple of things. One is lack of information among the decision makers about this technology. Two is the lack of facilities that can be used as a case study to really understand the economics and the real world challenges of operating this equipment and using this technology. And third is really the lack of equipment. I mean, as I said, for 30,000 cubic meters per day, I think in China, they're now having like 7 accelerators to deal with 30,000 cubic meters per day, if I'm correct. But you're talking about 1 million gallons, 200 million gallons per day. There isn't enough equipment available today to use it. So it's one thing to say that the technology has the potential. It's another thing to have the technology available today to make it a reality.
Yeah, thank you so much.
You're most welcome.
One more question.
It will be just not hello, Suresh Anche is just speaking.
Hello.
So congratulations on this presentation, because I think that it is the best lecture which are here in the field concerning this possibility of application. So I think beside of all these problems, the problem which you just mentioned about the accelerators, from my point of view, is the biggest problem, because as you know, we have already an industrial facility for flue gas treatment, with 1.2 megawatt accelerators, but now we are close to build also sludge treatment facility. But of course we need the high power accelerators, but also with high energy efficiency. So sometimes we are just choosing even for sludge 2 MeV accelerators, because these are the transformer accelerators with 80% electrical efficiency. So this is what we have to have in mind as well. So I think that we appreciate very much also, of course, your activities in the United States, but also to Omar and also our colleagues from Turkish Institute, that such conferences here, there is a lot of industry already. We had very interesting discussion, because here we have to have some speed up development of accelerators. I know that in the United States some laboratories are working now on this superconducting magnets application for accelerators. So even for linear accelerators, efficiency goes up to 80%. I mean electrical efficiency. So I think that, of course, if we would have good machines, I think that we may find partners in industry, but be honest with them that we just deliver the accelerators, because it is the most important component of the system, with good, let's say, efficiency, reliability, and of course we understand that in this case, in harsh industrial condition, this equipment has to work in continuous operation. So thank you very much. So once more, thank you for this wonderful presentation. Thank you.
Thank you, Professor Himalski, for your kind words. Yes, and you hit the nail right on the head, that there is the world all around. We really need better machines, more reliable, more robust, high volume, high power machines, high energy machines.
Thank you, Professor Pillai, your presentation and contributions.
Thank you very much, and have a nice rest of the day, ladies and gentlemen. Thank you.
Thank you. The next presentation comes from Dr. Uwe Goss. He's from Dresden Technical University and ASIS GmbH in Germany. He has 3 presentations. First is challenges in the use of electron beam in sorting of plastic waste. The second is challenges in recycling of carbon fiber reinforced composites. The third is preparation of high-performance polypropylene scrap, tire rubber composites by electron treatment. Can you hear me, Dr. Uwe? Dr. Uwe, can you hear me? We can see your presentation. Sorry. Yazabilir misin chatbox'a? You can open your voice, please.
Hello.
Hello. Welcome, Dr. Uwe.
Yeah, I can hear you. Yeah.
Yes, we can see your presentation. The floor is yours. Thank you.
Okay, then I will start. Thank you very much to the organizers to inviting me. It's a pleasure for us to present our activities in recycling of plastic waste, and also to give some information on the requirements for the recycling of carbon fiber reinforced composites. At first, I would like to start with the use of a low energy electron beam in sorting of plastic waste. First of all, I would like to give a short introduction to this topic. Then I will stress the state of the art, that means the electrostatic separation, and our approach to improve the electrostatic separation by the use of low electron beam pretreatment. At the end, I will give a short information on our planned project, which we would like to start next year. So, we have different types of polymers like thermoplastic, elastomers, and thermosets. And as you know, there are different methods of processing, different properties, and the polymers are not compatible. When we are looking to the plastic waste in the European Union, then we will see that polyethylene and polypropylene make about 50% of the plastic waste. And this is a challenge because we have until now no product-specific collection system. That means we have a mixture between polyethylene and polypropylene. And here you can see some consumer products for the sorting, and the separation of mixed plastic waste into its fraction is required due to the incompatibility of different polymers. That means during the melt mixing, you will have a separation and you will lose the mechanical performance, and so you can't apply polymer mixtures for high performance applications. So that means when we would like to use these mixtures, we have to separate, and in addition, and sometimes we also have to use reactive processing to enhance the interfacial adhesion between two polymer blends. And Mr. Zwickowski has shown in 1995 that the e-beam technology can be used in order to enhance the interfacial adhesion between polypropylene and polyethylene. But when we now are looking to the possibility to separate polymers by triboelectric charging, we will see that polyethylene and polypropylene belongs to polymers which can be not separated. And this is a problem. Until now, the electrostatic sorting is used for this type of polymers, which tends to a positive charge, or to the other part of the polymers, which tends to negative charge. So when we are looking now to the electrostatic sorting, then we have to take into account that we have different options. That means we can sort different polymers, and this is a dry separation process, and we have low sorting cost, and the throughput is up to 1 ton per hour. And separation of different polymers is independent from the specific weight and color and shape. And at the right-hand side, you can see the separation step. That means we feed a mixture of polymer A and B to a mechanical pretreatment. The mechanical pretreatment is required in order to ensure a high throughput in the charging system and separation system. Then we come to the charging and separation, and at the end we have the separation of the two plastics types. So here you can see the principle. That means, for instance, we have polycarbonate and ABS, and when we are doing the triboelectric charging, the polycarbonate gets positive and the ABS gets negative, and then we are feeding the mixer through the charging unit. Here we have the charging unit, and here we have a positive electrode. That means the positive charge polycarbonate will go to the left box, and the negative charge ABS particle will go to the right box. That means it works very good, and here we have a splitter. So here you can see the equipment of the company Hammers, which is used for the electrostatic sorting. That means the pre-treatment of the polymer mixtures which we would like to use have to be shredded, grinded, and dried. This is very important. If the humidity at the surface of the shredded particle is too low, that it's too high, that means we have a small moisture layer, we will not get the optimum result. We have also to remove the dust, and we also have to decharge, that means to neutralize the particles. And in most cases, these polymer mixtures come from the zinc flow separation step. And the restrictions we have for the separation is that we are not able to separate wet and dusty products. Also, it's not possible to separate foils because the weight to area is too low, and so we have a very low throughput. And the next is that we are not able to separate compounds. And also we have to take care on oily, greasy particles and also on fibers. And the treatment, or if the plastics contain some antistatic agent, these antistatic agents will also influence the triboelectric charging and might also have an influence on the separation. So, and as I already told you, there is a limitation for polyethylene and polypropylene. due to the molecular structure, we have hydrogen atoms and carbon atoms, and so we have no difference in the chargeability. And so there's a need for a new approach to use this electrostatic sorting. And the answer is that we can use electron treatment and not gamma irradiation. Why? When we are using electron treatment, then the electrons are transferring energy. This is the same like in the case of gamma rays. But in addition, they transfer negative charges to the atoms and molecules. And this transfer of negative charges was our idea, should be used for the separation. So here we have a short overview on the electron-induced chemical reactions. As you know, there is a curing, cross-linking, polymerization, main chain scission, shafting, and functionalization. And in the case of polypropylene, we have a very good chance to induce also functionalization. So, when we are now looking to the properties of HDPE, LDPE, LNDPE, and isotopic PP, that means the glass transition temperature and also the crystallinity. We can see that there is a very broad range for the glass transition temperature, and we have a well-separated glass transition temperature for these four polymers, and the crystallinity also differs sometimes. Not in the case of LDPE and LNDPE, but in the case of LDPE and LNDPE, we have different glass transition temperature. But what are influencing these two parameters? That means the crystallinity and the glass transition temperature influence the polymer chain segment mobility. That means if we have a crystal region, in this crystal region, we will have a reduced polymer chain segment mobility. And also, if we are working at room temperature, then we have a high polymer segment mobility for polyethylene, but not so for isotactic PP. And these two parameters are controlling the lifetime of radicals, and our hope was that it also controls the lifetime of trapped primary electron charges. So we did some experiments. Here on the right-hand side, you can see the surface energy after an electron treatment. This was done during the practical training of our students, and they measured for a long time the surface energy for modified and unmodified PP. Here you can see this part, dispersed part, and the polar part. Here, and the polar part is very high and decreases slowly over the years. This might be also an possible effect which could be used for the electrostatic sorting. We tested this. We used electron treatment and also plasma treatment. But when we are using electron treatment, we have to use a high electron energy to transfer a small amount of charges, and we have shown that the plasma treatment and the electron treatment with 10 MeV will not result in a separation of PP and PE. That means the functional groups which we are generating during the irradiation of polypropylene has no influence on the triboelectric charge. Another was that we would like to irradiate with low electron energy. Because when we are using low electron energy, we are transferring a high amount of charges, and there is the chance that the charges will be transferred to polypropylene and polyethylene, and then we have a special storage time. The storage time we need in order to get different negative charges of the irradiated polypropylene pellets and the polyethylene pellets, like I have shown here. And then we can go into the triboelectric charging, and the more negative charged polypropylene will go to the anode, and the negative charged PE will go to the cathode. So, and how we have tested this, we use an electron treatment of 0.6 MeV and the electron energy of 7.5 kilogram, and we measured the lifetime of the radicals, which is shown here in this figure. And as you can see, at the beginning we have a very fast decay of the trapped radicals, but then after about 1 to 2 hours, we have a very slow decay for the polypropylene, but the decay continues for LEP. That means from this, we took the information, might be after a storage time of 2 hours, we will see any, or we will have any chances to separate polypropylene and LEP due to different pre-charging by electron treatment. The crystallinity is nearly the same. We have strong differences in the glass transition temperature for PP and LEP. So here you can see the design of our experiment. That means we have worked on air. That means we have a charging unit. Here we have a high voltage system with anode and cathode, and here we have 8 boxes. And we use virgin pellets. One pellet, that means the LEPE was white, in order to enhance the determination of the separation factor, and the PP pellets were yellow. And here you can see that the irradiated LEPE was sorted into box 1 and 2, a little bit in 3 and 4, and the PP was mainly sorted into box 6, 7, 8. That means our idea works. So here you can see the result for the separation of LEP and PP. The storage time was 48 hours, and the separation factor amounts to about 99%. That means we have now improved the electrostatic sorting by the use of electron pretreatment with only 7.5 kilogram. But as you know, there are also there should be also some influence of the storage time, and that's why we tested at a storage time of 27 hours and 192 hours. And you can see our separation step works too. That means nearly independent of the storage time when we are looking for the range 1 day to about 7 days. The separation factor is high, it's about 99%. But when we are looking to most polymers, you know, the polymers are modified by pigments or by antistatic agent or by flame retardant materials or fillers. And we want to develop a separation method which is only sensitive to the property of the filler and not to the which is only sensitive to So that means we prepared some different compounds, LEP and PP, with pigments, antistatic agent, and flame retardants, and we produce pellets for our electrostatic sorting. Oh, no, it's not working. So, hello? Hello?
You couldn't skip another. Yes.
So now it's working.
Okay.
Yeah.
Now okay.
Okay. That means we have now tested this, and here we can see the test of LEP and PP containing flame retardants, and you can see the LEP is filled with a flame retardant, and the PP is not filled. Again, you have the separation of LEPE and PP, and then we have filled LEPE with another flame retardant, 48%, and PP was unfilled. Again, we are able to separate these two types of polymers. And in the contrast, it was also possible unfilled LEPE and flame retardant PP could be also separated. That means there is no influence of the flame retardant on the electrostatic sorting. Then we use some chalk, 40 mass percent of chalk into LEPE. Again, it was possible to separate from the unfilled. And then we have used the unfilled LEPE and filled PP. The separation was also possible. Then we have taken some talc, and also in the case of talc, you can see it here, a separation was possible. So we have shown that real polymers, which are filled or modified by some fillers or pigment like carbon black and chalk, or they have some surface contaminations, white egg, milk, sugar, and so on. All these polymers can be separated by electron pretreatment and electrostatic sorting. So, but now we have to do the next step. That means the next step is that we have to test real plastic waste and to know some packaging for the foodstuff I have shown here, and then we are shredding this. We have this type of mixture. Now this is a totally different requirement on our process, and we have started to test this in order to show that our procedure works again. And the project partner of the planned projects are the university, the Budapest University of Technology and Economics. This university is a project coordinator, then the University of Applied Sciences in Germany, Dresden, where I am working too, and the National Institute for Textile and Leather in Romania, and the company Monofil from Romania. And in the advisory board, we have 3 companies, one from Hungary and 2 from Germany. So the project aim is that we will produce high-performance composites from plastic waste. That means we want to use recycled polyolefins separated by our method, and we also would like to use rubber particles. That's why I will also speak about rubber particles in the over next presentation. We want to create a new design and new recycling strategies for polymer waste. That means we have to take into account the design from recycling and the design for recycling. When we are looking for the preparation of polymer compounds, we should avoid cross-linking in our polymer, otherwise we will strongly influence the recyclability. And the next one is that we also would like to validate this new procedure in the real environment. That means we would validate the TRL level 5. And for this purpose, we need the industrial facilities of our partners from the countries. And finally, we would like to make a comprehensive assessment of our new process. So, before we can start with the electrostatic separation, we have to do a pre-treatment, a mechanical pre-treatment. That means we have to remove the dust from the label, and we also have to remove thin films to enable a high separation process and a maximum throughput. And in addition, it is not possible to separate by viewing the particles. As I have shown before, we had white pellets and yellow pellets. Now we have mixed, and it is not possible to use a different scanning calorimetry because this is too time consuming. That's why we are using from the company Hamos the advanced sorting methods based on combined NER and short infrared imaging to sort the separated or to analyze the separated polymer types. But this technology will only work for light color plastics, and that's why we have used the packaging which I have shown to you. If the polymer is black, this method will not work. And finally, we tested our system without any electron pretreatment, and as you can see, we were able to handle this mixture, but without electron pretreatment, as we have expected, we have no separation of polyethylene and polypropylene. And the aim of the project next year will be to build up an electron pretreatment facility for higher throughput so that we can test this method. So, at the end, I will give short information on the cost. When we are looking for the material cost, which amount to about 1.5 euro per kilogram, then we will have a very fast amortization of the investment. It took about 1 year when we are producing 2,000 tons per year, and the electron pretreatment should be integrated between the pretreatment process, the mechanical pretreatment process, and the electrostatic charging and separation system of the company Hamos. So now I will come to the conclusion for my first presentation. We have shown that the pretreatment before electrostatic separation of polyolefins works. That shredded plastic polyethylene, polypropylene waste can be transported through electrostatic separation after dry pre-cleaning, and the enhanced electrostatic separation can be used. That means offers the possibilities to separate dark polyethylene and polypropylene mixtures into a variety of products and environmental rehabilitation. So I would like to thank my colleagues, and I also would like to thank Denmark and the IAEA for the organizing of this nice workshop, and you for your attention. Thank you. Hello?
Dr. Uwe, you can continue with your second presentation.
Are there any
Can you hear
questions
me?
to the presentations or not?
Challenges in recycling of carbon fiber reinforced composites.
Okay, then I will start with the next presentation.
Yes, you can continue.
Yeah, okay.
You can share.
So can you see my presentation?
Not now.
Yeah,
No, you can't share now.
but I had opened the
Yes.
presentation.
Yes, you can open. The floor is yours. Thank you.
So the second presentation, which is not connected to the use of electron beam treatment or to the use of gamma irradiation, has the title Challenges in Recycling of Carbon Fibers Reinforced Composites. At first, I will give a short introduction to the others GmbH. Then I will give a motivation for the use of carbon fiber reinforced composites. Then I have to give some information on the production of carbon fibers and carbon fiber reinforced composites in order to understand why the recycling of this type of material is so difficult. And then I will come to the state of the art in recycling of carbon fiber reinforced composites. And at the end, I will give some short conclusions. So the others company was founded in 1998. We have contacts to more than 30 countries worldwide. We are certified by ISO 9001 and by TSEX, and we are offering a full program from one hand, and we have experiences in inline e-beam facilities for the modification of precursor fibers. As you know, when we are producing high-performance fibers, we are starting from the polymer fiber, and after the preparation of the polymer fiber, mainly by wet spinning, we have to transfer the polymer into ceramic structure, and this is done by a high temperature process, and the temperature goes up to 1,300, 1,800 degrees Celsius, and thus we have to stabilize the precursor fiber, and this can be done by electron beam technology. So I would like to start with history. As you can see here, the first work was done in 1881. It was a patent from Edison. He wrote a patent for the use of carbon fibers for the production of lamps to generate light and bring some light in our life when the sun is not shining. And then you can see it's a very fast development, and the latest, it was in September at the Technical University, the world's first building was taken into operation. This building is constructed by carbon fiber reinforced concrete. That means you see that there are increasing applications. And so we should ask why engineers are looking for the use of carbon fiber. The answer we will find here in this table. Yeah. Carbon fibers have, when we are comparing glass, aluminum, and steel, the highest modulus, the highest tensile strength, and the lowest density. That means here we have a high potential for the production of lightweight materials with high mechanical performance. And then there are also some other properties, like the high short-term dynamic properties and the very good vibration damping properties. That means carbon fiber can pick up a high dynamic load, and so it is possible in combination carbon fiber and epoxy resin, you are able to prepare a high performance carbon fiber reinforced composite. And at the beginning of my presentation, you have seen the chassis of the BMW E3, and this chassis is produced using carbon fiber and epoxy resin. Epoxy resin, when we have cured, then we have thermosets, and you know thermosets are not able to reprocess by melt mixing. So here you can see some applications, and the total market for carbon fibers in 2020 were 145,000 tons. And the market are aviation and space industry, mobility and transportation. Then we have the wine industry, sports, construction, and others. Here you have some applications. So before I will come to the recycling, I have to give some information on the production line. That means we are starting from a filament. Yeah, that means we are wet spinning the precursor fiber. Then we have the stabilization, which can be also done by electron treatment. Then we have the low temperature carbonization, high temperature carbonization. Then we have the sizing. The sizing is very important. You can see it here. Because we have to generate a very good interfacial adhesion between the fiber and the matrix in order to transfer the load from the fiber into the matrix and vice versa. And then after the sizing process, we will prepare some rovings. And these rovings will be used in two different ways. First is that we will produce some textile semi-finished products, like you can see it here, or we will use the textile finished products and we will prepare some pre-packs, like you can see here. And here you have a first application of the recycled carbon fibers. BMW and the company Polynt in Germany have met an agreement that the Polynt company is using the production scraps for the preparation of the textile semi-finished products for the E3 and the E7 to prepare SMT material. And this SMT material filled with carbon is presently only used by BMW. And I will also give some applications for this. This is one way how we can recycle carbon fiber material. So after we have finished this, then we have to cut the pre-products. We have to make a trapping, the fixing, and in this case, we have to do the impregnation of the resin. And here we only have cutting and trapping. So when we have finished this one, then we have the consolidation. Since we are using, in most cases, we are using the thermal curing. That means we have produced thermosets, and during the thermal curing, we are also generating the interface adhesion between the fibers and the matrix. And at the end, we have to test. We have to test the material, and here we can see an test device at the IMA, and here you can see a rotor blade from a wind generator. That means when we are looking to this production cycle, the carbon fiber reinforced composites have an enormous potential due to their durability and lightweight, and they enable, and this is also a problem for the recycling, they enable the production of complex shapes. That means there is no restriction. Yeah, you can produce any product with any geometry, but this makes the recycling very, very difficult. So then the next point is, I have shown here, is the performance of the carbon fiber reinforced composites as function of the relative fiber length. Relative fiber length is the ratio of the fiber length to the fiber diameter. And the diameter of a carbon fiber is less than 10 microns. That means of the filament, of one single filament. And when we are looking here to the relative fiber length, then we can see that for short fiber, we have nearly the option that we can use the full potential for the E modulus, but not for the strength and the impact strength. And we need at least this fiber ratio to use the total options of the carbon fiber. And that means carbon fibers are mainly used in continuous fiber reinforcement structures and in unidirectional continuous fiber reinforcement. That means we need long fibers and not short fibers. This I will stress later. And in addition, we also need some assembly. That means the carbon fiber products should be connected to other materials, like I have shown here in the BMW 7 series. Here you have reinforcement element on the roof, and here you can see some connections. But when you are using carbon fiber reinforced structure, you cannot only drill. This is not possible, because then you will damage your performance. That means you have to use a special design or some special tools in order to prepare the hole where you can make the connection. Or there are some inserts. These inserts has to be put into the system where you can connect the carbon fiber reinforced part with other material. And nowadays we have this triangle. That means we need high performance, safety, but in addition sustainability. What does it mean? It means that we have to ensure a high efficiency for the use of raw material and energy, and we also have to minimize the waste production. And for the future, it is also possible to enhance the scalability and the production cost. Until now, the methods which are used in the production of carbon fiber reinforced products, they have a low scalability, and I have also shown it at the beginning. The applications are aircraft, automotive industry, but only BMW. That means where or other companies which are producing not more than 30,000 or 70,000 cars per year. if you look to Volkswagen, or to Toyota, then it is very difficult to have a process which is able to produce more than 1 million carbon fiber reinforced products for the automotive industry. But the main concern and the main challenge is recyclability. And when we are looking, and here was a very good publication, I think in 2018, something like this. There was done a forecast for the carbon fiber reinforced waste. Presently, we are in this range. There is a low amount of waste, but this amount of waste will start or will increase in future, and the origin of the waste is production scrap. Here there are some ideas I also have shown to you. The use for reinforcement elements in the car industry, and we have now the end of life for some short life applications, high volume applications, or long life applications. This will come within the next year. So that means that these challenges we have to overcome, these are related to technical aspects and economical one. And one is also that the industry needs more specific legislation for the change to an efficiency recycling as an alternative to landfill disposal. That means the manufacturer should be responsible for the recycling of its products. This year we had a lightweight conference in Dresden, and we asked Volkswagen if they have any idea how to organize the recycling of the cars and also the fiber reinforced parts of the cars. And the answer was very simple. Our cars are going out of Germany, and the recycling will take place out of Germany. This was the answer. That means that's why we need more legislative, that the manufacturer is responsible for the recycling of its product, because he knows the composition and the construction of the product. And it's also very important that the manufacturer will take into account the recycling process. That means he has to change from the normal engineering to a design from and design for recycling. Yeah? This is very important. This is also which we have to introduce in the carbon fiber reinforced composites. And the future market of the carbon fiber reinforced composites will increase. I have shown this. Yeah? And we have to make critical assessments for the state of the art of presently used recycling technology in order to identify which methods can be used for the future. There are different recycling methods, primary methods I have already mentioned. Here you will find the SMC product, which is produced by the Polind company. That means you will see it in the C pillar. Here you have a reinforcing part of the BMW 7 series. In the secondary mechanical recycling, there you are using various stages of scrap size reduction. That means this is more or less a downcycling because we are reducing the fiber length. Please remember the figure I have shown to you. That means when we are reducing the fiber length, we are not able to have or to use the full potential of our carbon fiber. And then we have the tertiary, that means this covers thermal and chemical processes and it depends on the way of recycling. And there was a presentation of Mr. Kajiwara from the Shenzhou University in Japan 4 years ago in Dresden, and he has shown that he took 1 meter times 1 meter carbon fiber reinforced composite plate, which was loaded, and after the loading, it was handled by pyrolysis, and the carbon fiber were tested, and the carbon fiber showed reduced mechanical performance in the order of 10% less tensile strength. So there are some commercialized recycling facility in UK, Germany, and USA. They are doing the carbon fiber reinforced composite recycling by pyrolysis, and they have about 2 to 2,000 tons per year throughput. When we are now looking to the mechanical recycling, we have the problem that the typical size of the recycling is less, not larger. It's less than 10 millimeters. That means we only have short carbon fibers and carbon fiber powder. That means we have low quality fiber recyclate, and there is a limited market. The shortcomings I have mentioned here. We have downcycling, but there is a hope that with enhancing this throughput, we will reduce the energy consumption, and so it might be possible that we can use a large-scale milling process for the production of short fiber or powders. So the chemical recycling, when we are using a solution, the solution is peroxide and hydrogen and dimethyl formamide, then we have recycled carbon fibers with nearly the full carbon fiber properties. This is good. But the shortcoming is that it takes a long time. But there are some other methods, like supercritical methods, where they are using supercritical water, and the hope is that this technology can be transferred to industrial scale and then can be tested for the recycling of carbon fiber reinforced composite. And here we have the thermal recycling. We also have a reduction in the carbon fiber properties, and this limits the application of these recycled fibers in high-end application. So we also have another one. That means the fluoride is bad. This is only a test in UK, and the main shortcoming is a high reduction in tensile strength and stiffness, and so it makes until now no sense to use these recycling products for high-end applications. So that means we can summarize the reuse of carbon fiber reinforced composites. The value strongly depends on the mechanical performance and the fiber length of the recyclate. If I have good fiber length and nearly the same mechanical properties, then I can use it instead of virgin carbon fibers, and I have a high cost reduction. Otherwise, I have a very limited market, or I will find a lucrative market. And here was a publication this year that the shells and shear webs for rotor plates, wind turbine plates, can be produced by recycled carbon fiber, and this makes also sense because 20 to 90%, they have better environmental performance. That means the conclusion for this topic is that we have high durability of the carbon fiber reinforced composites due to the thermoset. We have a very complex reinforcing structure and inserts. Yeah? And mainly we have a reduction of the mechanical properties and the fiber lengths. There are only one method until now, the solution methods, which will give fibers with good lengths and also with good mechanical properties. That's why we need enhanced communication and collaboration between researchers, industrial companies and governments for developing advanced recycling methods for carbon fiber reinforced waste. So, then thank you for the attention and also thanks to the organizer. And if I'm going right, I should now present my last presentation.
Continue with your third presentation.
Yes, I will do.
Now we can take a coffee break.
So,
Okay, thank you.
you are welcome. So, now I will come to my last presentation, as I have already mentioned.
Dr.
in my
Ghost, can
first
you hear me?
presentation.
Dr. Ghost, can you hear me?
Yeah. Yes,
now
I can hear you.
Now we take a coffee break. After break, we can continue with your third presentation.
Okay, we will do so.
Okay.
That means the comment
nearly
will
15 or
take,
20 minutes. We have a break time.
Okay, thank you.
Okay, see you again. Please continue with your third presentation. Thank you.
Yeah, thank you. I
stage
hope
is yours.
that you enjoyed your coffee break. Now I will give my last presentation on the
Yes.
topic scrap tire rubber composites by electron treatment. So I will give a short introduction and the motivation. Then I will come to some specific requirements. That means the selection of the adhesion promoter and the test of the multiple recycling. And at the end, I will give a principal facility design for the production of this product. So here you can see a processing plant for the recycling of plastic. These are thermoplastics where you can use the waste material. You have a shredder, then you have a washer, and you have different types of separators, mechanical dryer, and also the thermal dryer, and then here you have the extrusion. And we can, or we know the primary recycling. This is a re-extrusion. That means you have some scrap during the production, and you will reuse these scraps during for the production of products. Then you have the secondary. In this presentation, I will focus on the secondary. That means the mechanical recycling, tertiary and quaternary recycling. So the aim of the recycling is that we will use our consumer products. In this case, are the tires from lorries. We have some waste, we have to sort, pre-process, mechanical recycling. We need some reactive modification. Here we use the electron treatment. Then we have a new feedstock, and this new feedstock we will use for the production of our consumer product. Very important is that in the case of mechanical recycling, we need the separation of the plastic waste into its polymer fraction with known recipes. Yeah? That means it is very fine, or it would be the optimum case if we are using product-specific waste streams or sorting, and we need some reactive processing for overcoming the incompatibility in the interface between different polymers or polymer and filler. And here in this presentation, the filler is the rubber particle. That means we need some specific agent, crafting agent, for the preparation of our product. Motivation is in Europe, you have several companies which are dealing with rubber and with the recycling of rubber. One of these companies is in Saxony, near to Dresden. It's called Müssner Recycling Company, and from those companies you can get well-specified rubber particles or rubber powder in a reproducible way, and you have some data sheets with information on polymer content, type, and so on. And this was our motivation to test these rubber particles for the production of new products. Yeah, we know one process. That means this is a dynamic vulcanization. During the dynamic vulcanization, you are transferring a blend, that means a blend of a thermoplast and a rubber, into a thermoplastic vulcanisate. And you have a fast inversion, and you have to cross-link the rubber phase. Here you will see one cross-section. That means here we have the rubber phase, here we have the matrix phase, national rubber, and the matrix phase is polypropylene, for instance. When we are looking into this region, that means the rubber phase, then we have here the rubber molecules, and here we have the polypropylene molecules. And during the dynamic vulcanization, we have to do two processes. That means here the cross-linking of the rubber phase. And we also have to generate the yellow points. We have to generate some craft links from the rubber phase into the thermoplastic phase. And the idea was we will use rubber particles, not these big rubber particles, because we know that the size of the rubber particles is also controlling the mechanical performance. That means we use fine rubber powder and polypropylene, and we will mix it and will produce a compound which can be used for different applications, like you will see it here, like ceilings and so on. The problem is that the rubber particles, these are vulcanized rubber, and you have no functionalities at the surface for any matrix coupling, and without any enhancement of the surface activity. That means by a suitable coupling agent, you will not get an enhanced adhesion. Another possibility is that you will make a surface activation, but we will concentrate on the selection of a suitable coupling agent. The idea is the same figure like I have already shown. Now we have here our rubber particle. Yes, we have already a cross-linked rubber structure, rubber phase. Yeah. What we have to do is we have to generate these craftings between the rubber particle and the PP matrix by electron beam. Yeah. And we are using different types of cross-linking agents. Oh, here some mistake in the format. But we have tested 4 different rubber crafting agents, and these crafting agents should not lead to a cross-linking of the PP matrix. That means they should go into the interface between the rubber particle and the PP matrix, and they should show a high interfacial crafting at low dose. So here you can see the composition which we have tested. Yeah, at first the rubber particle and the polypropylene in a 50-50 blend. Then we have used the diacrylate with 2 double bonds, and then we have used 2 further crafting agents with 3 double bonds, and at least 1 coupling agent with 4 double bonds. We prepared the pellets by the extruder, then we shaped tensile bars, we did the electron irradiation, and then the testing. The dose was in the range of 20 to 120 kilogram. And in all compositions, the number of double bonds have been kept constant. So here you can see the influence of the adhesion promoter. Here you have the diagram, the black line without any crafting agent. Then we have used the tech. The tech shows no improvement in elongation at break, and also in the tensile strength. Here you can see the morphology. There is no plastified region between the rubber particle and the matrix, and so we have no interfacial adhesion. Here we have, then we can see that the TMPTE gets or gives a little bit better tensile strength and also elongation at break. The same is for the bifunctional acrylate, but the best mechanical properties we have achieved with the 4-functional acrylate. At 40 kilogray here we have given this cell, and you can see here the plastified strength fibers or strands between the rubber particle and the matrix. That means we have a good interfacial adhesion. On the next figure, you can see some diagrams for the mechanical properties as function of those, and from these we selected 80 kilogray is the optimum dose for our modification. The dose has nearly no influence or only a very small influence on the modulus. So then we have fixed our testing procedure for the recyclability. That means we produce the rubber particle reinforced or loaded polypropylene compound with the DTMPE. Then we produced the tensile bars. We did the test. Then we did 10 times the shredding. Yeah. Then we have had flakes again, material, and how will be the mechanical performance. And the answer you can see here, the first one. That means this was the original preparation, 0, and then we did 10 cycles of recycling. Here you can see the modulus. The modulus is not changed within the uncertainty of our measurement. We have a small decrease in the elongation at break in the range of 25%, but this could be overcome by adding some small amount of crafting agent. Here you can see the experimental results for tensile strengths. The tensile strengths, yeah, you have a small decay in the order of 13% after 10 cycle of recycling, and the Sharpie impact strength slightly increases or keeps constant. That means our prepared rubber particle filled polypropylene blend shows good mechanical performance and good recyclability. And as I have mentioned in my first presentation, this result will be now transferred to the use of rubber particles and electrostatic separated polypropylene from post-consumer products in our project. And principal facility design, you can see here, we need some storage silo for the raw materials, we need an extrusion line, and after the extrusion line, we have to include an electron accelerator. It should be a 1.5 MeV electron accelerator because we need a certain penetration path. The width of the transport system should be in the order of 1 or 2 meters, and then you can irradiate the pellets, and at the end you can put this into the silo. Yeah, this was my last presentation, and here are some conclusions. We have shown that we can prepare rubber particle filled composites with high mechanical properties by using a suitable crafting agent for the interfacial crafting. So we have the chances to convert polymer waste, that means waste from the tire and sorted PP waste from packaging to produce new products, and so we have the chances for environmental rehabilitation and resource sustainability and material innovation too. Yeah, and I would like to thank my colleagues and also the organizer for organizing this nice workshop, and thank you for your attention. Are there any questions to my 3 presentations?
Thanks for your presentations and contributions. Is there any question? There is no question. Thank you.
Yeah, you are welcome.
Çalıştayımıza Gebze Teknik Üniversitesi Çevre Mühendisliği bölümünden Profesör Doktor Sayın Mahir İnce'nin demir çelik endüstrisinde açığa çıkan KOK atık suyunun arıtım başlıklı sunumu ile devam ediyoruz. Sayın Profesör Doktor Mahir İnce'yi kürsüye davet ediyorum.
Herkese merhaba. Ben de birazdan çelik endüstri atık suyunda bulunan toksik ve rekalsitrant kirleticilerin biyolojik arıtma ve iyonlaştırıcı radyasyonun beraber çalışıldığı, işletildiği projeden bazı sonuçlarla katkıda bulunmaya çalışacağım. Nerede acaba? Ha, tamam. Tamam. Teşekkürler. Harika. Sunumda öncelikle küçük bir giriş yapacağım. Arkasından atık suyun ışınlanması hakkında biraz bahsedeceğim. Daha sonra koklaştırma atık suyu nasıl oluşur, arıtımı metotları nelerdir, onlar hakkında bilgi vermeye çalışacağım. Daha sonra da TÜBİTAK projesi olarak yaptığımız anoksik oksidik MBR'ın iyonlaştırıcı radyasyonla olan arıtımında bazı seçilmiş sonuçlarla devam edeceğiz. Sizlerin de bildiği gibi nüfus artışıyla aynı zamanda hayat kalitesinin artmasını sağlayan bazı endüstriyel üretimlerden dolayı atık su karakterizasyonu sürekli olarak zorlaşmaktadır. Dolayısıyla klasik biyolojik arıtma metotları ve tabii ki diğer fiziko-kimyasal metotlar söz konusu kirleticilerin arıtılmasında yetersiz kalmakta. Tabii deşarj edilen bu kuvvetli rekalsitrant toksik kirletici içeren atık sular aynı zamanda içme sularının, sulama sularının da kaynakta kirletilmesine sebep olmaktadır. İyonlaştırıcı radyasyon yine daha önceki sunumlarda da geçtiği gibi özellikle enerjik elektromanyetik dalgalarla ya da elektron gibi parçacıklarla atık su içerisinde radikaller oluşturmaktadır. Aslında tüm arıtmayı yapan da atık su içerisinde oluşan bu radikaller. Şimdi tabii bu radikallerle beraber iyonlaştırıcı radyasyonun diğer arıtma metotlarına karşı önemli üstünlükleri var. Bunlardan en önemlisi güçlü indirgeyici ve oksitleyici reaktifler oluşturması. Burada özellikle indirgeyici türlerin, reaktiflerin oluşması iyonlaştırıcı radyasyonun diğer ileri oksidasyon metotlarına göre en önemli avantajını oluşturmaktadır bence. Çünkü hidroksil radikali oluşturan diğer arıtma metotları da arıtma teknolojide vardır. Bunlarda sizin de bildiğiniz gibi UV oksidasyon bunlardan birisidir. Elektrooksidasyon bunlardan birisidir. Ancak indirgeyici radikalleri oluşturması iyonlaştırıcı radyasyon için aslında yeni çevresel uygulamaları kapısı açabilir. Çevre mühendisliğinde de özellikle atık su arıtımında aynı ileri oksidasyon gibi ileri indirgenme diye de yeni bir araştırma alanı oluşma sürecinde. Dolayısıyla gelecek 10 yıllarda biz yoğunlaştırıcı radyasyonu ileri indirgenme uygulamalarında da görebiliriz. Söz konusu bu radikallerle beraber yoğunlaştırıcı radyasyon her türlü kirlilik ortamında, buna emisyon yani baca gazı da dahil, atık su da dahil, bazı çamur ve katı atık uygulamalarda dahil çok farklı giderme metotları oluşturmaktadır. Bunun da yine en önemli etkisi direkt olarak enerjik, elektromanyetik ya da elektron gibi parçacıkların materyal içerisine girici etkisi olmasından kaynaklanmakta. Ve kontrol edebilirliği, özellikle otomasyonla kontrol edebilirliği oldukça yüksektir. Bunun yanında çok farklı metotlarla ya da ekipmanlarla beraber çalışabilirliği önemli bir avantaj oluşturmaktadır. Yine daha önceki konuşmacılar da bahsetti. Klasik arıtma metotlarıyla kolaylıkla birleştirebilmektedir. Yine hatırlayacaktır dinleyiciler. Dün Çin'den katılan araştırmacı ilk endüstriyel ölçekli elektron hızlandırıcılar kurduklarından bahsetmişti. Orada da aslında elektron hızlandırıcı biyolojik arıtmanın sonrasında membran kirliliğindeki azaltmayı düşürmek için kullanılmıştı. Dolayısıyla sadece biyolojik arıtmanın önüne, sonuna ya da çamur digestion'dan sonra ya da önce olarak düşünmemek lazım. Direkt olarak enerjiyi atık suya ya da suya transfer edebildiği için enerjik olarak değişiklik yapılabilecek, özellikle kirleticilerde konvansiyonel sistemlerin yetersiz kaldığı durumlarda önemli bir şart değiştirici ya da non-equilibrium bir şarta kavuşması için kullanılabilir. Tabii burada yine diğer ileri oksidasyon metotlarında hidroksil radikali oluşturmak için bazı kimyasal ajanlar kullanılmaktadır. Ama iyonlaştırıcı radyasyonda buna gerek yok. Yine UV'de çok duymuşsunuzdur eminim. Titanyum oksit gibi ya da çink oksit gibi bazı ajanlar kullanılır. Ama elektron hızlandırıcıda ya da kobalt 60'da böyle ajanlara herhangi bir ihtiyaç yoktur. Yine az önce belirttiğim ve üzerinde benim de son zamanda önemli durduğum ileri indirgenmede de diğer metotlarla indirgeyici reaktifler oluşturulurken yine kimyasal ajanlar kullanılıyor. Ama yine sık sık söylendiği gibi elektron hızlandırıcının ya da iyonlaştırıcı radyasyonun bu tür kimyasal ajanlara ihtiyacı yoktur. Tabii elektron hızlandırıcının ya da kobalt 60'ın biyolojik arıtmayla beraber kullanımında rekalsitrant, toksik olan yani biyolojik olarak arıtılamayan kirleticilerin önemi ayrı. Çünkü çevre teknolojilerinde en yaygın olarak arıtma metodu biyolojik arıtma. Bu biyolojik arıtma içerisinde de yine aktif çamurun çok önemli bir yeri var. Aktif çamur bazı kirleticiler karşısında maalesef zayıf kalıyor, yetersiz kalıyor. Bu zayıf kalmasında da iki neden var. Birisi kirleticilerin mikroorganizma tarafından parçalamayacak kadar uzun zincirli olması. Diğeri ise kirleticiler içerisinde toksiteye sebep olan bazı kirleticilerin olması. Birazdan biz ilerleyen slaytlarda göreceğimiz gibi siyanür, fenol özellikle mikroorganizmalar üzerinde olumsuz etkisi olabilmektedir. Ama iyonlaştırıcı radyasyonla biyolojik arıtma öncesinde bahsettiğim bu kirleticiler mikroorganizmalar için daha uygun tüketilebilir hale gelmektedir. Aslında biyolojik arıtmada da bir oksidasyon gerçekleşmektedir. Biz kirleticileri giderirken oksidasyon ve redüksiyon mekanizmalarıyla gideriyoruz. Şimdi ama mikroorganizmaların enzimlerle gerçekleştirdiği oksidasyon oldukça zayıf bir oksidasyondur. Biz bu oksidasyonu özellikle oluşturduğu radikallerle çok daha güçlü bir oksidan teknolojisi olan iyonlaştırıcı radyasyonla desteklemiş oluyoruz. Aslında mekanizmanın genel tanımını böyle yapabiliriz. Şimdi dolayısıyla bu çalışmada da biz özellikle toksik kirleticisi çok fazla olan ve yine biyoteknolojinin yetersiz kaldığı ama kullanılmaya devam edildiği, çünkü başka alternatifi olmayan kok atık sularında yardımcı olarak kullanabiliriz. Kok atık suyu da demir çelik endüstrisinde yüksek ısıl değere sahip kömüre ihtiyaç duyulur ve bu kömürün oluşturulması sırasında yaklaşık 800.000 derece oksijensiz ortamda ısıtılması sonucu kok atık suyu oluşmaktadır. Bu kok atık suyu içerisinde az önce belirttiğim gibi önemli ölçüde siyanür, tiyosiyanat, fenol gibi majör konsantrasyonda kirleticiler bulunmaktadır. Ama bunun yanında bizim de yine projede takip edemediğimiz ama bundan sonraki çalışmalarda özellikle üzerine yoğunlaşacağımız mikro seviyede oldukça toksik kirleticiler bulunmaktadır. Bunların da en önemlisi literatürde benzopren olarak gösterilmektedir. Söz konusu kuvvetli oksitleyici olan iyonlaştırıcı radyasyonun da ayrıca bu kirleticilere olumlu yönde etki ettiğini, yapılarını bozduğunu tahmin ediyoruz. Dolayısıyla kok atık suları demir çelik endüstrisinde önemli bir problem olarak karşımızda duruyor ve söz konusu arıtma tesisleri en azından Türkiye'de birkaçını ben biliyorum istenilen verimde çalışmıyor. Ve arıtma tesislerinin genel giderme mekanizması da aslında uzun süre havalandırma havuzlarında tutulması. Uzun süre tutulduğunda inhibisyona uğrayan ya da toksik etki gören mikroorganizmalar bu toksik etkiyi, inhibisyonu söz konusu süreçte elimine edebilmekte. Ancak verimler hala deşarj standartlarını sağlayamamaktadır. Dolayısıyla iyonlaştırıcı radyasyon söz konusu atık sular için çok önemli bir mekanizma olarak ortaya çıkmakta. Literatürde ve endüstriyel ölçekte de kok atık suların arıtılmasıyla ilgili bazı metotlar vardır. Bu metotlar çok eski ve aynı zamanda da yaygın olarak kullanılan çöktürmeyi söyleyebiliriz. Absorpsiyon özellikle çöktürme ya da biyolojik arıtmadan sonra kalın kirleticilerin giderilmesi için yine yapılmaktadır. Hatta absorpsiyon aynı zamanda biyolojik arıtmaya, aktif çamura yardımcı olarak havalandırma havuzlarına da ilave edilmektedir. Böylece az önce bahsettiğim toksik ve inhibik kirleticiler aktif karbon üzerine absorbe olarak mikroorganizma ile teması azalmaktadır. Temas azalınca tabii olumsuz negatif etki de minimize olmaktadır. Yine kimyasal oksidasyon bir diğer tekniktir ama kimyasal oksidasyon artık eskisi kadar kullanılmıyor. Burada klorlamayı örnek olarak verebiliriz. Islak oksidasyonu atladım. Şimdi ıslak oksidasyon da aslında yüksek sıcaklıklarda ve basınç altında yine hidroksil radikali oluşturularak uygulanan bir metot. Islak oksidasyon da aslında yine biyolojik arıtmaya yardımcı olarak öncesinde kullanılabilir. Ama biz ıslak oksidasyonu yine laboratuvar ölçeğinde petrokimya endüstrisi için kullandık. Dolayısıyla biyolojik arıtmaya olan katkısı oldukça sınırlı. Yani iyonlaştırıcı radyasyonla yine rekabet edebilecek bir ölçüde değil. Koagülasyon ve çöktürme yine alüminyuma demirle yapılır ama yine kok atık suyu için oldukça yetersiz. Ozonlama da aslında bildiğiniz gibi bir plazma teknolojisi ama ozonlamanın oksidasyon kapasitesi hidroksil reaksiyonuna göre düşük. Dolayısıyla katkısı da oldukça sınırlı. Elektrokimyasal oksidasyon yine elektrotlara elektrik verilerek adından da anlaşılacağı gibi oluşturuluyor. Ama söz konusu teknoloji özellikle elektrot yüzeylerinde pasifizasyon yaparak, iletkenliği düşürerek oldukça başarısız olabilmektedir. Kok atık suyu gibi yüksek iyonik güce sahip, içerisinde pasifizasyona sebep olacak kireçlenme vesaire yapabilecek atık sular için yine uygulanması fizibil olmuyor. Geriye klasik arıtma tesislerin metotlarından ben buna membranı da ilave ediyorum. Çünkü membran da artık o kadar yaygınlaştı ki klasik diyebiliriz. Biyolojik arıtma ve membran teknolojisi kalıyor. Şimdi biz yine bu projede biyolojik arıtma olarak özellikle anoksik ve oksik mekanizmayı da içerecek bir biyolojik arıtma sistemi seçtik. Ama biz literatür taramalarımızda projeye başlamadan önce gördük ki söz konusu anoksik ve oksik mekanizmada kok atık suyunda çaresiz kalıyor. Dolayısıyla bu prosesi de destekleyecek ileri bir arıtma metoduna ihtiyacımız var. Tam bu arada işte iyonlaştırıcı radyasyon devreye giriyor. Söz konusu inhibisyona ya da toksiteye sebep olan kirleticileri biz diğer ileri oksidasyon metotlarıyla da yapabilirdik ama söz konusu metotların sürekliliği maalesef mümkün olmazdı. O yüzden süreklilik açısından da biz iyonlaştırıcı radyasyonu tercih ettik ve projede de iyonlaştırıcı radyasyon olarak yine Nüken laboratuvarında bulunan kobalt 60 kaynağını kullandık. Kobalt 60 kaynağında ışınlandıktan sonra biz atık sularımızı anoksik, oksik membran biyoreaktöre aldık. Şimdi bu tabloda da kok atık suyunun ilk sütunda karakterizasyonu görebiliriz. İlk satırda verilen yoğunlaştırıcı radyasyon dozunu görebilirsiniz. Bu ilk sütunda görülebileceği gibi atık suyun KI konsantrasyonu 5000 üzerinde. Evsel atık suda KI konsantrasyonun 500-600 ppm olduğunu düşündüğümüzde bunun oldukça yüksek bir KU değeri olduğunu rahatlıkla anlayabiliriz. Yine BOI konsantrasyonu 1500 ppm civarında. Normalde BOI'nin COD'ye yakın olması beklenir. O zaman söz konusu atık suyun biyolojik olarak rahat parçalanabilirliğini söyleyebilirdik. Ama burada da yine sütunun sonunda gördüğümüz gibi BOD bölü COD oranı 0,29. Dolayısıyla bu atık suyun zaten biyolojik olarak deşarj standartlarını sağlaması mümkün değil. Bunu sağlayabilmesi için ya sonuna nanofiltrasyon ya da ters ozmoz gibi bir membran ünitesinin gelmesi lazım ya da biyolojik arıtmanın hemen önünde COD değeriyle BOD değerini birbirlerine yaklaştıran bir mekanizma uygulamamız gerekiyordu. Biz de bu mekanizma olarak az önce söylediğim gibi yoğunlaştırıcı radyasyonu kobalt 60'ı denedik. Ve bunun içinde farklı dozlarda ışınlama yaptık. Ve optimum ışınlanma değerini, dozunu belirleyebilmek için de yine BOI bölü KI oranını kullandık. Yani biz BOI'yi ne kadar KI'ye yaklaştırabilirsek kendimizi o kadar başarılı olarak atledecektik. Dolayısıyla sizin de gördüğünüz gibi en yüksek BOI bölü KI oranımızı 20 kilogreyde gördük. Ve 20 kilogreyi biz optimum iyonlaştırıcı radyasyon dozu olarak kabul ettik. Ama biz yine biliyoruz ki söz konusu kuvvetli, toksik, kirletici içeren kok atık suyu bu BOI bölü KI oranıyla da maalesef biyolojik arıtmada verimli bir şekilde arıtılamaz. O yüzden biz BOI bölü KI oranını daha fazla da arttırmak için yine çalışmalara devam ettik. Şimdi 20 kilogreyde ışınlamada majör ölçekte toksik etki gösteren siyanür, çözülmüş siyanürü, toplam siyanürü ve tiyosiyanatı, bunun yanında fenolü de yine analizlerini gerçekleştirdik, takip ettik. Şimdi burada da görebildiğiniz gibi çözülmüş siyanür 20 kilogreyde oldukça azalmakta ama zaten konsantrasyonu da çok yüksek değil. Yani 2 mg bölü litre. Tiyosiyanat biyolojik arıtmasında, kok atık suyunun biyolojik arıtmasında oldukça problemli bir kirletici. Amonyakla beraber arıtmayı oldukça zorlaştırmakta. Çünkü ortamda amonyum iyonu olduğunda tiyosiyanatın arıtımı oldukça inhibe edilmektedir. Dolayısıyla tiyosiyanatın biyolojik arıtmadan önce giderilmesi biyolojik arıtmayı oldukça kolaylaştıracaktı. Biz de o yüzden tiyosiyanatı takip ettik. Toplam siyanürde Yine 4,5 mg bölü litreden 20 kilogramda 2 mg bölü litrelere geriledi. Ama siyanür ve toplam siyanür biyolojik arıtmada özellikle kok atık suyunda çok fazla problem teşkil etmemekte. Çünkü ortamda diğer ağır metallerde olduğu için söz konusu ağır metallerle kompleks oluşturuyor ve mikroorganizmaların sitoplazmasından ya da hücre zarından sitoplazmaya giremediği için toksitesi sınırlı kalıyor. Kok atık suyunun diğer meşhur kirleticisi fenol. Fenol değeri de oldukça yüksekti. 700 ppm'lere yakın. Yine ışınlamayla beraber 650 ppm civarlarında oldu. Hala yüksek. Ama mikroorganizmalar fenol konsantrasyonuna aktivize olabilmekteler. Dolayısıyla hali hazırda mevcut kok atık suyu biyolojik arıtma tesislerinde de fenol zaten sorunsuz olarak gideriliyor. Sadece havuzlarda atık suyun bekleme süresini arttırıyor. Tek problemi bu. Ama bekleme süresi artınca bu ne demek? Havuz hacminin artması demek. Havuz hacmi artınca blowerlardan çok fazla oksijen basma, dolayısıyla hava basma demek. Aynı zamanda daha yüksek kapasiteli su pompalarının vesaire kullanması demek. Dolaylı olarak etkisi ve zararı artıyor tabii. Şimdi 0,44'lük BOI bölü KI oranı bizim atık suyumuz için yeterli değildi. Dolayısıyla biz BOI bölü KI'ni arttırmak için atık su içerisine hidrojen peroksit ilave ettik ve hidrojen peroksitle beraber ışınlama gerçekleştirdik. Yine sunumun başında söylediğim gibi iyonlaştırıcı radyasyonda indirgeyici radikallerle beraber oksitleyici radikaller de oluşmaktaydı. Dolayısıyla bu indirgeyici radikaller ortamda oksijen varsa oksijenle reaksiyona giriyor. Peroksi ya da hidroperoksi radikaller oluşturuyor. Bu radikaller de yine hidroksi radikali kadar güçlü oksitleyici değiller. Biz bunları da hidroksi radikaline dönüştürebilirsek daha avantajlı bir oksitleyici ortam elde edecektik. Bu yüzden de hidrojen peroksiti kullandık. Yine hidrojen peroksitle de yukarıdaki ilk satırda görebileceğiniz gibi atık suya ilave ettiğimiz ve oluşturduğumuz hidrojen peroksit konsantrasyonları, yine en altta da BOI bölü KI oranını görebiliyorsunuz. Biz en yüksek BOI bölü KI oranı elde ettiğimiz 0,55'i optimum hidrojen peroksit ilave oranı olarak tespit ettik. Ve dolayısıyla %0,5 hidrojen peroksit ilave ederek biz en yüksek BO bölü K oranını ilave ettik ve atık suyu söz konusu dozda ve hidrojen peroksit oranında biyolojik arıtma sistemine almaya karar verdik. Ama biyolojik arıtma sistemine almadan önce optimum olan bu ışınlanma şartlarında yine siyanür, toplam siyanür, tiosiyanat ve fenol konsantrasyonlarının analizini gerçekleştirdik. Şimdi siyanür konsantrasyonu Şimdi toplam siyanür konsantrasyonu yine görüyorsunuz grafikte. Maalesef çok fazla düşmedi ama bizim için çok da sorun değil. Tiyosiyanat konsantrasyonunu neredeyse arkadaşlar sıfıra yaklaştırdık. En azından detection limitleriyle. Dolayısıyla bu bizim biyolojik arıtmamızı oldukça rahatlatacaktı. Yine çözülmüş siyanür konsantrasyonu da yine oldukça düşük. %0,5'leri düşündüğümüzde. Burada tabii siyanür iyonu bizim için çok önemli olmadığı için ve hidrojen peroksit ilave etmemiz demek aynı zamanda maliyet demek olduğu için de biz sadece BOI bölü KI oranını dikkate alarak %0,5 olarak karar verdik. Çünkü BOI analizi zaten içerisindeki kümülatif karakterizasyon değişiminin mikroorganizmalar olan etkisini gösterebiliyordu. Burada en önemli değişikliği ise biz yine tiyosiyanat gibi fenolde yaşadık. Gördüğünüz gibi fenol konsantrasyonu çok düşük değerlere kadar indi. Ama daha önce de söylediğim gibi fenol zaten var olan sistemde arıtılıyordu. Sadece işletme maliyetini de düşürmüş oluyoruz. Şimdi bu slayttan sonra daha çok çevre mühendisliği ağırlığı olan slaytlar olacak. Ve ben de terimleri biraz daha fazla kullanacağım ama bunu da elimden geldiğince basite indirgeyerek açıklayıcı bir şekilde anlatmaya çalışacağım. Şimdi biz ışınlanmış atık suyumuzu bir nolu tanka koyduk. Sonrasında peristaltik pompayla anoksik tanka verdik. Anoksik tankta da aslında indirgeyici şartları oluşturuyoruz. İndirgeyici şartlar oksidasyon redüksiyon potansiyelin negatife düştüğü şartlar. Eğer iyonlaştırıcı radyasyonda o indirgenme özelliği daha da geliştirilebilirse belki bu sistemlerin de yerini alabilir. Anoksik şartlar aslında biyolojik arıtmada kullanılan mikroorganizmaların havasının kesilerek, oksijensiz ortama alınıp kısa bir süre bekletilerek geliştirildiği, çalışıldığı bir sistem. Dolayısıyla burada özellikle halkalı yapıya sahip ya da elektron almaktan ziyade elektron vermekten ziyade elektron almak isteyen kimyasal yapıya sahip kirleticilerin giderildiği bir sistem. Çünkü yapıya elektron girdiğinde yapı bozuluyor ve sonrasında da parçalanması kolay oluyor. Ama aslında tam da yeterli bir sistem olmuyor. Çünkü özellikle kloraminler gibi bu tekstil atık suyunda çok da görülür. Kloraminler bazı aromatik yapıdaki tekstil boyalarının anaerobik bozulmasıyla yani oksijensiz ortamda mikroorganizmalar tarafından indirgenmesiyle oluşur. Ama kloraminler daha sonra anaerobik ortamda parçalamaya devam etmez. Bunu oksijenli ortama almanız lazım. İşte iyonlaştırıcı radyasyon bu iki mekanizmayı da sağlayabilir. Eğer buna dair yeni teknoloji uygulamaları gerçekleşirse çevre mühendisliğindeki uygulama oranı da kabul edilebilirliği de hızlı bir şekilde artabilir. Biz anoksik şartlarda iyonlaştırıcı radyasyonda yapıları bozulan ama tamamen mineralize olmayan ya da hiç bozulmayan kirleticilerin indirgen şartlarda bozulmasını sağladıktan sonra oksijenli ortama aldık. Yani bu 3 nolu tank en çok bilinen biyolojik arıtma sistemi, yani aktif çamur sisteminin içerisine filtre edilmek amacıyla membranın yerleştirildiği bir sistem. Dolayısıyla artık klasikleşmiş, NBR olarak da belki sıkça duyduğunuz bir sistemdir. Arıtımına devam ediyoruz. En sonda bu membrandan vakumlayarak arıtılmış atık suyu alıyoruz. Bu 12 nolu sistemde bizim hassas terazi. Hassas terazide de yine çevre mühendisliğinde önemli bir noktadır. Membranın filtre edebilirliği. Onu çalıştık. Tabii bu sistemden 2 tane laboratuvara kurduk. Birincisine kobalt 60'tan geçirdiğimiz atık suyu verdik. Diğerine de ham atık suyu verdik. Herhangi bir işleme tabi tutulmamış. Böylece ışınlanmış atık suyun biyolojik arıtma verimini ayrıntılı olarak hiç ışınlanmamış bir atık suyunun biyolojik arıtımıyla kıyaslayarak ve aynı zamanda bizim çevre mühendisliğinde oldukça önemli olan membran kirlenme özelliklerinde kıyaslama şansı bulduk. Bu da az önce şematik gösterimi verilen sistemin laboratuvar ölçekli çalıştığımız düzeneği. Şimdi burada da biraz çevre mühendisliği terimleri var. Burada anoksik, mesela ilk verdiğimiz reaktördü. Hacmi 6 litre. Ama oksik reaktörün hacmi 12 litre. Bunun sebebi de az önce belirttiğim nitrifikasyon, yani amonyumdan dolayı bekleme süresinin çok uzun olması. Böylece reaktörleri 2 kat yaparak bekleme süresinde uzatmış oluyoruz. Yine oksik reaktöre daldırdım ve membranın özelliklerini belirten terimler. İşte gözenek çapı 0,2 mikrometre ve membranın suyun süzüldüğü yüzey alanda 0,2 metrekare. Diğeri hollow fiber membran, yine şekilde görüyorsunuz ve PES'ten yapılmış, imal edilmiş bir membran. Yine bu recycling rate dediğimiz aslında oksik reaktörden anoksik reaktöre olan döngü diyebiliriz. Burada az önce bahsettiğimiz şartların aynı reaktör içinde sağlanamaması ve farklı indirgen şartlara gitmesi gerekiyor. Özellikle amonyaktan, nitrifikasyondan sonra oluşan, amonyağın giderildiği nitrifikasyondan sonra oluşan nitratın arıtımı için. Yine bir günde 1 metreküp aktif çamura beslediğimiz toplam KOI miktarını veren bir organic loading rate diye bir parametremiz var. Bunda 0,25 aldık tüm çalışma boyunca ve işletme sıcaklığı da mikroorganizmaların en optimum, en hızlı yaşamsal faaliyetlerini sürdürdüğü, üremelerini arttırdığı 35 santigrat derece olarak seçtik. 35 santigrat derece olarak seçmek bize mali açıdan herhangi bir külfet getirmiyor. Çünkü zaten kok atık suyu sıcak olarak çıkıyor. Şimdi biyolojik arıtma çıkışındaki kimyasal kirletici parametrelerin değerlerine bakabiliriz. Burada farklı SRT'ler var. O kafanızı karıştırmasın diye kısaca bahsetmek istiyorum. SRT denen şey aslında çamur yaşı. SRT arttıkça reaktör içerisindeki çamurun konsantrasyonu artar. Ama kok atık suyu gibi yüksek kirliliğe sahip atık sularda her zaman için yüksek SRT tercih edilir. Bunun sebebi de mikroorganizma konsantrasyonu yüksek olsun ve dolayısıyla kirleticilerle temas yüzeyi her bir mikroorganizma başına daha az olsun. Dolayısıyla biz de bunu bildiğimizden dolayı 3 farklı çamur yaşında çalıştık. Çamur yaşı KÜ'lerin giderim üzerinde çok fazla etkili olmadı. Şimdi ışınlanmış atık suyun KÜ değerini aşağıda görebiliyorsunuz. Yine 300 ppm 400 ppm arasında. Ama ışınlanmamış atık suyun çıkış KÜ değeri 600-700'ler civarında. Burada da biyolojik arıtmada önemli bir giderim parametresi amonyum. Ve yine kok endüstrilerinde, demir çelik endüstrilerinde oldukça problemli bir parametre. Burada da yine ışınlanmış atık suyun çok daha iyi giderim verimi sağladığını net bir şekilde görebiliyoruz. Bunun en önemli sebebi tiyosiyanat konsantrasyonunun çok düşürülmesi. Aynı zamanda yine önceki slaytlarda bahsettiğim içeride bizim de çalışmada takip etmediğimiz ama toksik etkiye sebep olan mikro düzeydeki organik kirleticilerin giderilmesi olarak söyleyebilirim. Çünkü nitrifikasyon bakterileri oldukça hassas bakteriler. Ortamda çok basit olarak aratılan arıtma tesisleri için söylüyorum. Bu belediyeler tarafından işletilen arıtma tesisleri dahil çok düşük karbon olduğu zaman bile toksik olmasına gerek yok. Karbon olduğu zaman bile nitrifikasyon gerçekleşmez çünkü bakteriler inhibisyona uğrar. TKN yine amonyum ve organik azotu gösteren bir parametredir. Yine ışınlanmış atık suda gördüğünüz gibi ışınlanmamış atık suya göre neredeyse 2 kat daha düşük çıkış konsantrasyonuna sahip. Yine toplam siyanür konsantrasyonu düşük olmasına rağmen yine ışınlanmış atık suda giderim oldukça iyi. Bu tabloda da toplu olarak reaktörlerin hem anoksik hem de oksik çıkışlarında elde ettiğimiz değerleri görebilirsiniz. Parantez içerisinde verilenler giderme oranlarıdır. Yine burada KÜ'de önemli bir fark görüyoruz. 2 katı kadar oksik reaktörü üzerinde duruyorum. Çünkü oksik reaktör aslında atık suyun arıtılarak çıktığı reaktör. Yine BOI oranları burada BOI'ler çok da karşılaştırmak doğru olmaz. Çünkü ışınlanmış atık suyun zaten BOI'si yüksekti. Oradan zaten daha avantajlı. Ama BOI'ler burada mikroorganizmaların üzerine düşen işi yaptığını gösteren önemli bir parametre. Yine TOK mineralizasyonunu kirleticilerin mineralize olduğunu gösteren önemli bir parametre. Yine 2 kat, yaklaşık 2 kat bir farktan bahsedebiliriz. Amonyum konsantrasyonu yine grafikten hatırlayacaksınız. Oldukça büyük fark var. Az önce belirttiğim gibi nitrifikasyon inhibisyon ya da toksiteye sebep olan mikroorganizmanın aslında biyolojik bir indikatörüdür. Eğer sistemde nitrifikasyon gerçekleşiyorsa aslında doğru işletiliyor diyebiliriz o biyolojik arıtma için. Burada da aynı durum söz konusu. Ve diğer kirletici parametrelere göre fark daha fazla. TKN keza amonyak gibi arıtma farklarına sahip. Diğerlerinde de yine söz konusu bu saydığım parametreler kadar olmasa da önemli farklar, arıtma verimi açısından önemli farklar bulunmakta. Bu çalışma da TÜBİTAK tarafından desteklenmişti. Yine çalışmada yer alan diğer araştırmacı arkadaşları da slaytta görebiliyorsunuz. Sol taraf Gebze Teknik Üniversitesi'nde yer alan arkadaşlar. Sağ tarafta da Nüken'de yer alan arkadaşlar Ömer Bey, Ece Hanım ve Özge Hanım var. Özellikle Ömer Bey ve Ece Hanım'la projenin ilk yazım aşamasından beri beraber çalıştık. Hem yazım aşamasında verdiği fikirlerle hem de daha sonraki çalışmalarla her iki araştırmacı da önemli katkılar sundu. Burada hem Gebze Teknik Üniversitesi'ndeki projedeki araştırma arkadaşlarıma hem de Nüken'deki araştırma arkadaşlarıma teşekkür ediyorum. Ve benim anlatacaklarım bu kadar. Sorunuz varsa alabilirim. Yok herhalde.
Sayın İnce'ye sunumu ve katkıları için teşekkür ederiz. Küçük bir duyuru yapacağım. Sonrasında teknik geziye devam edeceğiz. Seher Çelik, Yetkin Erak Çora, Cafer Ergin, Melike Nurgül Gergin, Serkan Gürleyen, Sümeyra Mavi Şahin. Onlar bilgilendirme masasına uğrayabilirlerse gezi öncesinde memnun oluruz. Görüşmek üzere. Teknik gezi sonrası yemek molası vereceğiz. Yemek molası sonrası 2.20'de tekrar 2'de oturumumuz tekrar başlayacak.
Şu an internet mi? Ha, o yüzden bağlanmıyor. Bu da bağlantıyı kaybetti.
Öğleden sonraki oturuma hoş geldiniz. The next presentation comes from Dr. Lalit Varshney, Senior Scientist at Bapha Atomic Research Center and Director of Sludge Hydrogenization Facilities. The presentation is Radiation Technology for City Sewage, Dry Sludge Hydrogenization Technology and Feasibility. And the second presentation is the use of treated biosolid as organic fertilizer. Dr. Varshney, the stage is yours.
Good afternoon, ladies and gentlemen. And it is nice to see you after good lunch and tiring visit, although it was all interesting. At the outset, I would like to thank the agency for giving me this opportunity to have traveled 6,000 kilometers and then come to this place to share some of our experience in sludge hygienization and other scientific activity. I also thank Dr. Omar who did so much for us and took great care of us and organized this seminar. So I will talk something about a subject which is relevant to everyone. And sometimes these words, radiation, food, and shit, all together they don't go. People just don't like talking about this subject. But this is very important to everyone. This is the title of my talk. And since there is no internet, so my voice may modulate little bit here and there. So we all know environment is a big concern, whether Professor Kamilevsky, Dr. Suresh Pillai and other colleagues told that environment is really becoming a big issue. And climate change, water pollution, solid waste, space and air pollution. And all due to human activities. They were not there a century ago, but they are all here and keeping us busy finding solution for these problems. Now, if I see what we have to do, we have to plan for another 10 years or 12 years. Now, see, Delhi, India will become the largest populated city with 43.35 million. And that way you see even Japan is second, going to be 36.01 million, Tokyo. That way if you see, there are cities which are going to be highly populated by 2035, although they are now, but the pace will go up. And if we see we all use water. And about 1 trillion liters of sewage is produced throughout the world. And I have calculated 200 liters per person. And about 4.2 billion people live in cities. So that's how this figure of 1 trillion has come. And from that 1 trillion sewage, we produce about 1 billion ton of sludge. Now you can see this humongous amount. Quality and quantity of sludge indicates health of water treatment facility and the city. If you analyze sludge, you will find out about the health of the city. If they are into drugs, you will find many drugs in the sludge. If they are clean cities, you may not find anything into that. And sewage to become, in future, sewage to become water resource for economic activity and sludge for soil fertility. Finally, we are more than 7 billion people, we eat, we live, we drink. So water is slowly getting dried up and these kind of sources will become available for use. Now talking about India, we produce about 38,254 million liters every day, sewage. Now this is quite large. And about 7 million tons of sludge produced every year. And by 2040, this sewage will be 133,000 million liters every day and 24 million tons of sludge by 2040. Now what to do with this kind of waste material? It's a big question that we may have everything, but we may not treat all this kind of waste material in affordable manner. Now the Turkey is not visible, only population is visible. So country, Turkey population is 84.3 million. Istanbul is the largest populated city with 15.5 million. Ankara is 5.66 and Izmir is 2.5 million. Now let us see how much this, and we can presume that 22 kilogram dry sludge is produced per person every year. So that way, Istanbul produces 934 metric tons per day, Ankara produces 341 metric tons per day, and Izmir 150 metric tons per day of sludge. So these values I calculated, and this is how much we are producing. And if there is a gas production, then these values may reduce by another 25%. So we can say that Izmir definitely produces 100 tons of dry sludge every day. Now what is being done? I don't know. Omar may be able to explain what is being done with the sludge. This is the sewage treatment plant, which everybody might be knowing. I won't go into details. This is the drying bed that after treatment we put sludge into drying bed, or even from filter press we get this kind of black mass which is highly infectious. Now what is being done for this sludge? It is either disposed in unregulated manner, which is a health hazard. It forms hills and heaps, sold to farmers in unregulated, unhygienic manner at throwaway prices for agriculture application. I mean, these are the general trends, which are practiced by most of the countries. Now, what is being done world over? More than 50% is utilized in agriculture. With treatment or without treatment, it is being used. Most of the developing countries do not treat. How much pollution and health issues caused by this practice is difficult to estimate. Treatment will definitely improve health and pollution standards. Converting it to usable manure will do value addition to this waste. I mean, these are the practices being followed world over. Now, what are the major concerns with this sludge? There are heavy metals, pathogens, organic toxin. It is a big problem to dispose this infectious matter. I mean, the moment the word sludge comes, people become conscious. What is it, good, bad, or should we use it, should we not use it? Now, what is being done today, and what are the options available to municipalities? I mean, finally it is the responsibility of municipal corporation to dispose this sludge. So either they can pasteurize, which Dr. Pillai said in the morning, which is expensive, which is really expensive process, to use heat generating chemicals like calcium oxide. Calcium oxide reacts with water, produces heat as well as increases pH. So the pathogens can be taken care. But this is good for a small quantity of sludge. Sun drying, but this requires large area. But in India, a lot of sunshine is there, so this is a preferred method. And radiation, now it is coming up. It's not that radiation is being used for the first time for sludge treatment. First plant was made in Albuquerque, New Mexico, USA, but they were using cesium-137, so there was hue and cry, and within 4 or 5 years the plant shut down. And there are other R&D facilities in Germany, Brazil, Argentina, where they use this on small scale. And in India also, in 1992, we had liquid sludge cobalt source treatment facility, and this all, not many places it is being practiced. And this you all know, I need not explain how radiation is, it is a brand that it can deactivate living cells by direct and indirect interaction with DNA. So this I will just skip. Now, I don't know, the top line doesn't come. Anyway, so what are the concern about this sludge is, and how radiation interact with it? See, radiation kills pathogen, reduces smell, degrade chemicals, kill weeds, allows inoculation with useful bacteria. Now, if you know these 5 application or usefulness of treating sludge with radiation, you will appreciate that it is one of the best method. Because if STP is there, you can smell it from a kilometer that some STP plant is there. So that smell is gone. Other is weeds. If people use sludge without treatment, then these weeds grow along with the crop, and that is not desirable. Then we can inoculate it with useful bacteria. I will come in detail afterwards. Now I will come to our Indian plant which was made in 1992 to 1994, and it was a pilot scale facility to hygienize liquid sludge. This is how it was done. Liquid sludge was taken from a tank to the cylinder, this chamber, where you can see the circular rods of cobalt 60. It was falling from the top and then coming down to another tank. So that's how we were irradiating liquid sludge, which contained 3 to 4% of dry matter, and gave 3 kg of radiation dose to hygienize. But what was the reason that this technology did not multiply for 25 years? See, Dr. Sunil Sambarwal joined IAEA and I came at his place. And that's how I started looking why this plant did not multiply. Because it requires about 12 million kilocuries of cobalt 60 to treat 100 tons of Vadodara sludge which is produced every day. Recontamination due to open sun drying. The cost of treatment per kg is about rupees 6 to 7. So whatever rupees you divide it by 4, it becomes Turkish lira. So you can see that the technology did not multiply because industry people, government people, if they calculate what is the cost to treat this, although it does the job, but the economics doesn't work out. And the quantity of cobalt 60 requirement is huge. So what we did, we thought that we have to solve the problem of sludge. Then why treat liquid sludge? Why not solid sludge? So we put the plant after drying the sludge. And that's how this idea came, and we started working in 2015 what to do about it. Then immediately we did experiments. We took 25 kilogram of bags and put them in tote box in a radiation plant and keeping dosimeter at minimum maximum dose. Then we also put microbiological dosimeters to see if what the changes are there. We find even at 6.85 or 9.03 there is no E. coli, and then the log, there is about reduction of 4 log cycle, which we consider as sufficient dose to hygienize. It is not sterilization. We are saying hygienize. Nature is kind enough that pathogens are generally less in number in all this kind of material. So if we reduce bacteria by 4 log cycle, pathogens are generally eliminated or they are not there. So in this kind of dry sludge hygienization, we see the treatment cost is rupees 1 per kg. I mean, it is reduced by 1/5. And then chances of contamination are nil because we are irradiating and then packing them. And to treat 100 tons per day, it requires only 1.5 million curie instead of 12 million curie. And can be inoculated with plant growth promoting bacteria. I will come back to this thing. So there are several advantages of hygienizing dry sludge, and which is more affordable than sterilizing liquid sludge. And the liquid sludge was tried in Germany and many other places. And probably this technology did not multiply there also. So based on this concept, now we are operating 2 facilities of 100 tons per day. One facility is in Ahmedabad, which started in 2019, and the second one has come up in Indore city, which came in March 2022. So I can say that these are the only 2 facilities which have started recently throughout the world. These are the only known operational facility in the world. There is no other facility which is using sludge hygienization using radiation technology. So we have seen that in Turkey we have population which generate from 100 tons to 500 tons per day, and These cities have industry and are major source of heavy metals in sewage and sludge. Actually, sludge should not contain heavy metals, but because of the industry, they put their output line to sewerage, and that's how lot of heavy metal contamination is there in sludge, and becomes a very big question mark in the mind of public. More than radiation, they are worried about heavy metals. So how can we reduce these heavy metals in the sludge? First, to control the polluting sources, which may or may not be possible, or minimize the use of sludge. But if we minimize, then the benefits of sludge cannot be reaped in. So what we did, we integrated sludge hygienization technology with bio-NPK, so that this is nothing but a consortium of bacteria, nitrogen and phosphate solubilizing, this kind of bacteria which are inoculated in the sludge, and this becomes a sort of biofertilizer. Now we see that sludge contains arsenic, cadmium, chromium, copper, lead, mercury, nickel. I mean, these are not coming from human fecal, but they are coming from other sources. Now US EPA 40 CFR 503 has some limits, that kilogram per hectare per 365 day period, they should not exceed. These values are in kilogram, 2 kilogram, 1.9 kilogram, and these are some of the limits. And these limits are very different from European limits, which are much less. Now, the Ahmedabad city where we have put this facility, we analyze the sample and we see, for example, cadmium is present from 1 to 16 milligram per kg. I mean, sludge is a material, the composition of which keeps varying. So it's very difficult to say how much it will contain. So we can just find out the range at which it contains. Now, if we apply this sludge 3 tons per hectare per year, I mean 1 ton, we can assume there are 3 crops in a year, so we are putting only 1 ton per hectare in one crop, so 3 tons per hectare in a year. We find it is only 0.0015 in comparison to 2 kilogram. I mean, if we use 1 ton per hectare, then the quantity of this contaminating material is much, much smaller. So basically the sludge becomes very safe. And then we are inoculating it with bio-NPK. These are spores. So what happens? Recontamination is reduced like anything, because they will not allow other bacteria to grow into it. So this is the fundamental about inoculation. Now we also calculated, for example, cadmium which was present in the sludge. So 1 ton per hectare if we see, then we are putting 16,000 milligram per 10 more than this square feet. And if we calculate, divide, we get only 1.6 into 10 raised to power 5 milligram per kg of soil, which is very negligible concentration. And critical limit for soil is 5.9 milligram per kg. And cadmium concentration in natural soil is 0.01 to 2.7 milligram per kg. Practically, there is insignificant increase in cadmium concentration in soil by use of this treated sludge. So if we use this quantity with bio-NPK, the soil or crop contamination is almost negligible. But if you use 5 tons per hectare, 10 tons per hectare, then the heavy metals may move to the crop fruit. And I have assumed that the soil density is 1 gram per cc and the metal distributes because of the sludge is only 1 foot deep. And by using this kind of material, the value of health benefits and environment protection cannot be calculated. So at one side you are getting a biofertilizer, and moreover you are recycling the waste material, which will give you health benefits and environment protection. And this is what the Ahmedabad, the first facility which was made in 2019, which is 100 metric tons per day, and it cost about $4 million. The total project, which is about 70 million Turkish lira, and 2 years is the project time. If you want to establish, then it will cost this much, and that's how. convert waste sludge to manure, protects health and environment, provides organic carbon to soil, saves subsidy on urea. I mean, don't look at how much it costs to treat with radiation. If you see the benefits in totality, they are much, much larger, which can be calculated. For example, our government gives subsidy on urea, 15 rupees per kg. The cost of this is only 21. 15 rupees is given by government as a subsidy. Now, if we can replace part of this kind of fertilizer by this material, government saves a lot of money, and every year they can put such plant. So we tried to convince these government agencies, municipal corporation. They agreed to put their money. We did not spend even a single rupee, only provided technology know-how and hand-holding, and they spent all their money to manufacture this. So what are the benefits of this project is, this is the first time in India, farmers will give pathogen-free, hygienized, enriched fertilizer with high organic carbon contents, rich source of macro and micronutrients. And this kind of thing will be very good for European countries. Hygienized, enriched fertilizer will improve soil health and productivity and protect health of people living in urban areas from high load of potentially infectious microorganisms. I think you have seen even SARS, COVID and all viruses, bacteria, pathogens are there. So it is really a beneficial project, and we have started this, and 2 more such facilities are coming soon in India. And they have registered the name of this treated sludge as BioGold. So they have registered this trade name for their product. And this is how, see, it was, I really don't know myself how I did all this job together, that inspiration or passion was there. We started meeting ministers and all municipal people. And this lady is the Chief Minister of Gujarat state. And this is me. And this is how we started this plant. And then our chairman, Dr. Vyas, is there, who used to visit this facility when it was under construction. So everybody supported this program, that yes, it is good and we should go ahead. This is the pool which was erected. When we make such facilities, the first thing is to erect a pool, water pool. And this I will just show you what are the different, how it started under construction. This is the roof plug. Inside the cell, these are the machinery which was started. And I think this is the water pool where the source was there. This is the crusher. This is the cyclone separator. I will talk about it. And this is the source which when it was loaded in March. And this was the inauguration which was done in 2nd March 2019. And this is how the facility looks like. And this facility was, when operational, people from different states started coming, because everybody want to see the first facility. And that's how the mayor of another city came to visit this facility, and we convinced them that's how useful it is for the national program. And then we signed this memorandum of understanding with that government, how they can put the plant. And this is the second plant in Indore city. Now this is the cleanest city in our country, ranked number 1. And this sludge hygienization facility has some 20 points. So when they calculate, these 20 points are added for them. So there were technological challenges also, because it was dry sludge. There was dust generation, which is contaminated, impurities like stones, metal, plastic, wood and paper, hardness of the cake, particle size control, inoculation with bio-NPK, bagging and sealing, and all this were taken care by use of technology which is commonly available. Then there are 2 important questions were asked by my department. Who should spend money for such a facility? If yes, then gamma or electron accelerator. Then we know that it is the responsibility of the government or municipal corporation to dispose this sludge. And the initial capital cost to be preferentially met by government. As I said, government is responsible, and by sale of this manure, the payback period is 8 to 10 years. I mean, you will get all money which is invested in 8 to 10 years, and recycling of waste is there, and so many other benefits which I described. Now we are building large number of sewage treatment plant, because in our country we are about 40 to 45% sewage is only treated, rest 55% is still untreated. So we are building large number of this plant, and we have the cost of such facility is only 7 to 10% of the what we make for STP plants. So if somebody is building STP plant, they can include this cost into the manufacturing of such facilities, and then it becomes part of the facility. And this is how we are promoting in our country to set up such facility in sewage treatment plant. But how many such facilities we can have? And here the question of use of electron beam accelerator comes. We cannot have so much cobalt-60. So maybe after 10 facilities we have to switch over to electron beam accelerator. But there are also some issues with electron beam accelerator, but that can be solved. Now, if the sludge output is only 50 to 100 tons, it is better to go for gamma. And if it is more than from 100 to 600 tons, then accelerator will be a better choice. And this is with respect to Indian situation, because cobalt is quite cheap in our country, about $1.2 per curie, and that's how we are able to do it. Now 2 more facilities are coming up, and I hope the work will start soon. And if you see the techno-economic feasibility of this sludge hygienization is, and we require only 1500 square meter of land. Cell area is 350, storage area is 1500 square meter. And these are the plant and machinery like conveyor system, source holding, embedment, DMRO plants, ventilation. I mean, these are such subsystem of the facility which are required. And then sludge handling, because it is the bulk handling, so we require sludge collection hopper, crushers, box tilting system, cyclone separator, throw mill, which is a sieving system, needed, and forklifts, etc. So many subcomponents, machinery and required which is there. Then you require about 19 manpower also, like facility in charge, radiological safety officer, plant operator, quality control officer, lab assistant. See, another problem is getting staff for this kind of facility. Although we have program to certificate RSOs, radiation safety officers, but number of facility in our country is about 30 irradiation facilities are there. So these RSOs are too much in demand. So we have started a course in university to certify RSOs. Then if we see the total cost, land we are presuming it is available, civil is about 80 millions, plant and machinery 70, cobalt 60 is the highest cost, PGP production and dosimetry. My total cost is about 275 million Indian rupees. So you divide it by 4, roughly you will get Turkish lira. So this is situation is in our country. And we calculated if we process 50 tons per day or 100 tons per day, what is the cost per ton? This for 50 ton it is coming 1500 rupees per ton, and for rupees slightly more than 1000 rupees per ton for if we are processing 100 tons. So roughly in 1 Turkish lira you can process 4 kg of sludge, which is a biofertilizer. And if you buy from market, it is available for 20 to 25 rupees per kg. So you can see the treatment cost is 1 rupee and we can sell it for 5 rupees. So naturally it is a profitable business for municipal corporations. So they would like to invest. Government is benefited, municipal corporations are benefited, so they will put their money. And they are getting so many other things. So when radiation technology helps common man, atom smile. This is my slogan. when we actually help common people, then only atoms smile. So this kind of projects cannot be completed without the support of various agencies. We have Ahmedabad Municipal Corporation who invested their money, then BARC from where I come, then source was supplied by BRIT, Board of Radiation and Isotope Technology, then Indore Municipal Corporation and CIMEC engineers from Bombay who made this dream come true sort of thing. And support of our chairmen, Dr. Shekhar Basu, Shri K.N. Vyas and Atomic Energy Commission, they were always with us to support. So it was a big project, but we completed in 3 years. And everything was, because this was the first project, the second project came in 2 years itself. So now things are streamlined and many can be protected. Now this is the Ahmedabad plant that I have shown, and what is going inside I would like to show. I don't know how to click the movie, it is hyperlinked to this. Can you run the movie please? So this is the plant machinery and equipment. You will see what exactly is there inside. Sound? Sound is not coming. This is the solar power. Has stopped again. The bio NPK production. So this was all about the machinery and equipment which are present inside this facility, which is fully automated. The sludge goes inside and the bag of biofertilizer comes out. So there is no human interaction in between. So this is how it started. May I close it, please? You can start my second presentation. Sorry, because I am told that time we spent in site visit and this dosimetry lab and accelerator. So different from